Am I audible? Yes. हाँ हाँ हाँ, अच्छा।
একটার সময় করতে হবে তাই তো? আচ্ছা আচ্ছা। আচ্ছা তুমি কি বেরিয়ে যাবে নাকি? আচ্ছা আচ্ছা, ঠিক আছে ঠিক আছে ঠিক আছে, সমস্যা নেই। ঠিক আছে ঠিক আছে। Good morning, all.
Thank you, Dr. Dash. Good morning, everyone. Today is the second day of our FDP course. Today's program will start with the lecture of Dr. Santosh Bishwas. Dr. Bishwas is an associate professor of Department of Mathematics, Jadavpur University. I request Professor Bishwas to deliver his lecture.
Okay. I thanks to the organizer. I also especially thanks to Dr. Krishna Bordas for invite me. I something problem. I am unable to present this button is not working. Now I skip and rejoin. Okay. Uh, am I audible?
Yes, yes,
Is it visible?
yes.
Also sensible, I think.
Uh,
Okay, okay.
okay, okay.
Good morning, all of you. Myself, Santosh Vishwas, working as associate professor in the Department of Mathematics, Jadavpur University. The title of my talk is Continuous Dynamical System and its Application. I try to cover all these topics. All these topics are necessary for clear understanding about the dynamical system of the difference in terms of differential equation. The notion of a dynamical system is the mathematical formalization of a general scientific concept of a deterministic process. The future and past state of many physical, chemical, biological, binomial, and even social systems that can be predicted to a certain extent by knowing their present state and laws govern their evolution. If it is applied in continuous system, then it is called continuous dynamical system. And if it is applied in discrete system, then it is called discrete dynamical system. Now, the formal definition. The formal definition of a dynamical system is trivial. Say capital T, X, and phi t. T is the time set, X is the state space, and phi t is the evolution operator. And this phi t is a mapping from X to X, and phi t satisfied two group properties I not equal to id. That means if we are putting the value t equal to 0, then this is equal to id. Id means identity map on X. And another, if phi t plus s equal to phi t composition phi x. That is, the evolution operator satisfied phi t plus s if it is operate on x, and it is nothing but composition of two functions, and obviously this is satisfied for all values of s and t, and x belongs to capital X. Now we consider an autonomous system. Now if we consider a system of equation of this form, say x dot equal to f of t comma x, and if we assume say x belongs to r to the power n. See here, if the system explicitly depend on the time variable t, then it is called time dependent or non-autonomous system. Now, if t does not explicitly occur in the equation, then it is called autonomous system. Next, for the autonomous system, we define the equilibrium point of the system. That means if we consider x dot equal to only f of x, t does not explicitly present in the equation, then it is autonomous system. Then the equilibrium point of the autonomous system is defined by, if you discuss x naught, then f of x naught, this is equal to 0, then we get the equilibrium point. That means the equilibrium point is nothing but we putting say x dot equal to 0, and then we get all the equilibrium points of the, if we solving this one. Okay. Next, when we consider a system of differential equation, then existence and uniqueness theorem is also important for important, because see here x dot equal to fx, say x dot equal to fx, this is a system of equation. Therefore, if we consider say x belongs to r to the power n, if E be an open subset of r to the power n containing say initial point say x0, and if f belongs to C1e, then we can say that there exists a real number a such that this system has a unique solution, and we can get the solution exists and as well as unique for t lies in between minus a to plus a. Next, we consider a linear system. Now, see here in the linear system, that means if we consider a system of differential equation, say x dot equal to fx, if f is linear, if f is linear, then it is called a linear system. For simplicity, we consider say x dot equal to ax is the linear system, where capital A is the n cross n matrix, and x naught belongs to r to the power n is the initial value. Then the unique solution is given by say e to the power at into x naught. This is the unique solution of the system. See here, already we assume that say f belongs to C1e. C1e means continuously differentiable up to first order. That means all partial derivatives with respect to the variable say xi, where I equal to 1 to n. That means if we consider x belongs to r to the power n, that is all partial derivatives are continuous, then obviously the solution exists as well as unique. And this is nothing but this is x dot equal to ax, is a system of linear equation. Then obviously the solution exists as well as unique. And if we try to prove of this theorem, then first we want to show that ddt of e to the power at equal to a e to the power at. And for proving this one, we first, if we consider two transformation, like say s and t are two linear transformation, and obviously if st equal to ts is true, then we can say that e to the power s into e to the power t equal to e to the power s plus t. Then easily we can get the result, say ddt of e to the power at equal to a e to the power at. And then we can, if we differentiate, and that means x naught e to the power at x naught is satisfied x dot equal to ax. Then we can say that the solution of the differential equation exists. Then we can easily we check the solution of the system as unique. Next, we consider a coupled linear system. Now, what is the coupled linear system? For simplicity, if we consider the two linear equations, say x dot equal to ax plus b and y dot equal to cx plus d. That is, see here in the x dot equal to ax plus b, the left hand side is a dx dt, but right hand side is a function in terms of x and y. Similarly, in y dot, the function again the combination in terms of x and y. Therefore, this system is called coupled system because left hand side is a derivative with respect to x, but right hand side is a combination of x, y. If it is only x, then we can say that the system is uncoupled or decoupled. For simplicity, we consider this system. See here, x dot equal to minus y and y dot equal to x. That means this is a coupled linear system. Now, sometimes say if we consider a coupled linear system, then we are unable to determine the solution of the system in analytically. But if we take the advantage of the linear algebra, then we can get the solution is very easily. And in the diagonalization is nothing but diagonalization means if we consider a system of a system of coupled linear differential equation, then diagonalization can help this coupling system to convert to an uncoupled system or decoupled system. That means diagonalization of a square matrix is a technique for reducing the linear system to an uncoupled linear system. Now, for this, say x dot equal to ax, and if we try to diagonalize, this theorem is very useful. First, we assume that all eigenvalues of the matrix capital A are real as well as real and distinct. Then we consider a vector in the form say v1, v2 up to vn. This is the basis in r to the power n, and the matrix P is also invertible. Then we can get P inverse of AP is diagonals of lambda 1 to lambda n. Now, if we try to convert x dot equal to ax, this is a coupled system. This can be converted to an uncoupled or decoupled system. Then we consider a suitable transformation. Now, for the transformation, say y equal to P inverse of x. And if we consider this type of transformation, then we can say that y dot is nothing but P inverse of AP to y. That means here P inverse of AP and A, they are similarity matrix. And then see here in this frame of reference, y dot equal to something into y, this is a decoupled system. If it is a decoupled or uncoupled, then we can get the solution very easily. Because x dot equal to only function of f of x, then you can easily solve it. Then in a converse way, again we can convert the x equal to say py, then we get the solution of the systems in the original frame of reference, that means coupled system. Now we define the phase portrait. Phase portrait is nothing but phase portrait of a dynamical system is defined by the set of all solution curves in the phase space of r to the power n. Now we consider a two-dimensional say system x dot equal to. Any question? Is there any problem? Now see here x dot equal to ax is a linear system. Where matrix capital A defined by this and x is equal to x1, x2. That means we consider the two-dimensional system. And two-dimensional linear system, and obviously this is a coupled system. Then we first trace the number of equilibrium point of the system, and number of equilibrium point of the system. Number of equilibrium point of the system is to depend on nature of the matrix capital. That means if the rank of the matrix capital A equal to 2, then only one equilibrium point, that is trivial equilibrium point, exists. And if rank of A equal to 1, then A1x and A2, that means two vectors are nothing but they are linearly dependent. Then we can express the two equations in terms of only single equation. Therefore, the line of equilibrium point exists and which is passing through the origin. And when rank of capital A this is equal to 0, then if we choose any point in the plane, this is the equilibrium point of the system 1. Now, we explain the stability theory. We assume say Wj equal to Uj plus Ij Vj is a generalized eigenvector of the matrix A corresponding to the eigenvalue lambda j equal to Aj plus I. And we consider B in the form say U1, U2, Uk up to Uk plus 1 and up to Um be a basis of r to the power n, where n equal to 2m minus k. Now see here 2m minus k component. Now in the first U1 to Uk only the single component, but they are Uk plus 1, Dk plus 1, they are in a pair. That means we assume first k component, that means lambda 1 to lambda k, the eigenvalues are purely real number, whereas uk plus 1, that means jk plus 1 to m, their eigenvalues are complex conjugate. Then we form a basis B. This basis, that means the subspace R to the power n, and obviously n equal to 2m minus k. This subspace can be subdivided into three categories. One is called a stable subspace. Stable subspace is nothing but the span of uj vj when eigenvalues, real part of the eigenvalues are negative quantity. Whereas unstable subspace is defined by a span of the vectors where eigenvalues, real part of the eigenvalues is positive. When eigenvalues are purely imaginary, then we get a central subspace. Therefore, obviously, if we consider any space in R to the power n, then R to the power n is nothing but union of ES, EU, and EC. Now, according to the fundamental theorem of the linear system, and we get the solution nothing but xt equal to e to the power at x naught. That means solution passing through the point x0. Therefore, motion of the point x0 belongs to R to the power n along the trajectory 1 described by the mapping e to the power at is a mapping from R to the power n to R to the power n. Now, we trace the all eigenvalues. If all eigenvalues of the linear system capital A are defined from 0, real part should be defined from 0, then the flow is called the hyperbolic flow. And obviously, if the equilibrium point is called hyperbolic equilibrium point. As well as the system is called hyperbolic linear system. Now, similarly, if all eigenvalues with a negative real part, then it is called sink. If all eigenvalues are positive real part, then it is called source. If we calculate all the eigenvalues, at least one eigenvalues are positive and at least one eigenvalue negative, and the equilibrium point is hyperbolic, then you can say that the nature should be saddle type behavior. Now we consider a planar autonomous differential equation. Any problem? Okay. Now x dot equal to x, and obviously see here this is a coupled system, and we assume the matrix A is simple. That means none of the eigenvalues are not a zero value, and obviously the matrix capital rank of the matrix A equal to 2. Then we consider a suitable transformation. Then this linear system, that is coupled linear system, can be converted to a uncoupled linear system, let's say y dot equal to jy, where j equal to P inverse of A. That means here we have already told you the matrix A and P inverse of AP, they are similar matrices. Then if A is simple, and obviously simple means eigenvalues are different from 0 and as well as non-singular, then the Jacobian matrix has one of the following form. That means two eigenvalues are real and distinct, then we get the form 1. If two eigenvalues are real and equal, then we get these or another one, say lambda, gamma, 0, lambda. If two eigenvalues are complex conjugate, then we get the Jacobian matrix of this form. That means here see, observe that when two eigenvalues are real and distinct, that means we can apply we can take the advantage of linear algebra. Then we can get this form, diagonalization form. But in the when two eigenvalues are equal, then we cannot, that means coupled system becomes again coupled. Again, see here, for this is a coupled system, if two eigenvalues and purely imaginary, not purely imaginary, then we get again the coupling system. Now we consider the first one, say this system. Now say this is a decoupled system, then we get the solution is nothing but y1 dot equal to y10 e to the power lambda 1t, and similarly we get y20 equal to y2t equal to y20 e to the power lambda to t. That means we can write the solution in this form, combination of two bases. Next, see here, when two eigenvalues are negative. Obviously, when two eigenvalues are negative, then y1 tends to 0 as t tends to infinity, whatever the initial value of c1. Similarly, y2 tends to 0. But see here, when we choose two eigenvalues are negative, but lambda 2 more negative than lambda 1. In this case, the eigenvalues lambda 2 is a stronger eigenvalue, whereas lambda 1 is a weaker eigenvalue. In this case, y1, y2 both converge to 0, but y2 rapidly converges to 0 than y1. Then we can get the solution of the trajectory in this form. Again, we trace what happened at t tends to what happened at the point origin when t tends to 0. Now, if we can write and say y2, that means say y2 equal to something into y1 or y2 by y1, and then we can get, say, as t tends to infinity, and where lambda 2 minus lambda 1, lambda 2 is a stronger eigenvalue, then as t tends to infinity, it becomes tangent. That means y2 equal to 0. That means the trajectory, all this trajectory near the point, very close to the point 0, 0, it becomes tangent like this one. Therefore, the trajectory, whatever the initial value, it may be first quadrant, second or third, fourth, all trajectory should be tends to 0 as t tends to infinity. Now we trace the axis. When y2 equal to 0, then we get y1, whatever the initial value. Initial value of either may be positive, may be negative, but always tends to 0. Then this type of behavior is called stable node. Conversely, if two eigenvalues are not negative, they are positive, then if this inequality true, then arrow should be away from the origin. That means the all trajectory away from the, this is a, no, here lambda 1 is a more stronger eigenvalue than lambda 2. In this case, the trajectory near the point t equal to 0 becomes this axis. Therefore, we get again the stable node. But when if two eigenvalues are positive, when two eigenvalues are positive, then we get the unstable node. Here the arrow should be always away from the origin. This is wrong. This is away from the origin. Next, on this figure, if the two eigenvalues are positive, then we can get the unstable node, and all trajectory starting very near the point origin, but they can go away from the origin as t tends to infinity. Now, what happens if two eigenvalues are in opposite side? And see here, when we choose a lambda 1 negative and lambda 2 positive, then obviously y1 tends to 0 as t tends to infinity, but y2 tends to 0 as t tends to infinity. That means if the trajectory is start here, then we try to reach this one, but this is the away from the origin, then trajectory should be this. Again on the axis, when we consider these axes, then see here lambda 1 negative, this is towards the origin, but lambda 2 positive, then it is away from the origin. This is the saddle behavior. And obviously this is on the saddle type nature around the equilibrium point. Next, we consider when two eigenvalues are equal and Jacobian of this matrix in this form, Jordan form like this form. Then we get the solution in this form. And we can write y2 dot by y1 dot equal to c2 by c1 plus gamma by, this is a lambda, not delta. And obviously this is tends to 0 for positive infinity when gamma positive, and it is goes to negative infinity when gamma negative. Therefore, see here, when lambda negative means two eigenvalues are same and they are negative sign, obviously this is stable nature. And depending on the value of gamma, when gamma positive, then trajectory should be here to here. Now I clear why trajectory like this. Now see here, in this y2 dot by y1 dot is nothing but a slope, that means tan theta. Therefore, see here, when gamma positive, then it is goes to positive infinity. Now tan theta positive on the first and third quadrant. Therefore, see here, it is a tan 90 degree. That means the trajectory should be a start to here, and always it becomes at the 9 pi by 2 angle around there. That means if it is starting here, then you get here. Similarly for that. Now see here, when we get lambda positive and gamma negative. Now lambda positive means y1 and y2 always away from the origin or diverge to infinity. But to see here, when gamma negative, then tan theta, that means this quantity goes to, tan theta should be goes to diverge to negative infinity. Then we get the trajectory like this. Now, if we choose, say, gamma equal to 0, if gamma equal to 0, then again we get the two eigenvalues are equal, and we get nothing but like this. That means when lambda negative, the behavior around the equilibrium point and any trajectory starting at they are always straight line towards the origin, because this is stable, and this nature is called stable star, and this is called unstable star, and away from the origin. Again, this the arrow should be away from the origin. That means next see here, again j equal to alpha beta minus beta alpha. That means we first starting with coupled linear system, but two eigenvalues are complex conjugate, then we can get again coupled system. That means we cannot convert to a decoupled or uncoupled system. In this case, we first try to convert this system Cartesian to polar form. In this polar form, if you explain it, otherwise we can take another technique. Now here we consider the Cartesian form to polar representation, and we that says this system is nothing but y1 dot equal to this and y2 equal to this, and we consider the polar representation or polar transformation, say y1 equal to r cos theta and y2 equal to r sin theta. Then this system reduced to r dot equal to alpha r and theta dot equal to minus beta. That means depending on the values of alpha and beta, and we can get the dynamics of the system around the equilibrium point 0, 0. Now see here, when alpha negative, then RT decreases and decreases to 0 as t tends to infinity. But when beta positive quantity, then we can get solution of theta t equal to minus beta t plus theta naught. That means initial trajectory started with theta naught, then it is diverged to negative infinity. That means it is a clockwise direction. Therefore, see here in this figure, when if it is starting here, then it is a clockwise direction, and our radius should be decreases and converges to 0. That means this type of behavior is called stable focus, whereas this is called unstable focus. Now, if we consider a time series representation or this one, then see here is nothing but initially, say radius increases, then damping oscillation, and finally it is converges to 0. Now, whatever when alpha positive and beta may be positive, may be negative. Now here alpha positive. If it is alpha positive, then obviously RT should be increases as t increases. Therefore, it is diverged to infinity. Now, depending on the values of beta, then we can get sometimes clockwise direction, sometimes anti-clockwise direction. And see here the amplitude of this is increases. That means diverge to positive infinity. Now, if alpha equal to 0, beta may be positive, beta or negative. That means alpha equal to 0 means the RT, the radius should be constant, and depending on the sign of beta, the may be clockwise or maybe anti-clockwise. And this type of nature is called neutrally stable nature or and this is the time series representation. Now, all these type of behavior can be summarized in the following theorem. That means if we consider say tau equal to trace A and delta equal to determinant A, then we have the system x dot equal to Ax. If delta negative, then it is saddle at the origin. If delta positive and capital delta defined by this one, then we get the origin is a node type of behavior and it is stable with tau negative and unstable tau positive. That means all these can be summarized in the previous all the informations. Now see here the diagram. Now see here tau square equal to 4 delta. That means we draw a parabola like this, and this is your tau axis. Tau x-axis represents the trace and y-axis represents the determinant delta. Therefore, see here when delta negative, that is the characteristic equation is nothing but delta square minus tau delta and lambda square minus tau lambda plus delta. That means product of two eigenvalues are negative when delta negative. Now see here, two eigenvalues are negative means it is always saddle behavior. That means in the third quadrant and fourth quadrant, the equilibrium behavior of the equilibrium point is saddle type behavior. Now see here in this. Now this is the parabola, and below the parabola, and we can get capital delta should be a positive quantity. If capital delta is positive quantity, then two eigenvalues are real and distinct. As well as tau negative, that means two eigenvalues are real and distinct as well as negative. Then we can get the stable node behavior. Now, in the above, in this region, capital delta, this is a negative quantity, and capital delta negative means two eigenvalues are imaginary with a real part negative because tau negative, real part negative, then we get the spiral behavior or focus and obviously stable focus behavior. But on the curve of parabola, here two eigenvalues are same with negative, then it is stable star. Similarly, in the first quadrant, and we can get the unstable behavior. Therefore, second quadrant always represents the stable nature around the equilibrium point, but it is defined for different region. That means if it is region, it is a spiral behavior, it is a stable node, and it is stable star. Next, nonlinear system. Similarly, if f t comma x we consider a nonlinear, that means if f is a nonlinear. Again, if t does not explicitly occur, then it is called nonlinear autonomous system. And obviously, in the previous we defined the phase space in the nonlinear system. Next, we try to check the flow. That means flow, evolution operator phi t or flow operator. This flow operator is satisfied to group properties or not. Now, for this, we consider a system say x dot equal to fx and fx is equal to b. This is a coupled as well as nonlinear system. Now we try to determine phi t and check phi 0 equal to id and these two group properties satisfied or not. Now see here for this, we can get the first equation nothing but this is a decoupled system and you get the solution very easily. And similarly, in the second, we can get the solution. That means the flow operator or solution passing through the x naught is given by this expression. Now see here if we put in say x1 0 equal to 0 and y2 equal to 0, then easily we get phi t 0 0 equal to 0 0. That means 0 0. That means equilibrium point, or it is called fixed point. That is nothing but this is the fixed under the mapping phi t or under the flow phi t. Therefore, the flow operator phi t is passing through any arbitrary point. This can be defined by this one. Now we check phi s of phi t, and after some algebraic calculation, and we can easily check that the two first group properties, that means the second these group properties satisfied. Now we check the first group properties. That means if we put in t equal to 0, if we put in t equal to 0, then we get this. Therefore, two group properties satisfied. Next, linearization. That means see here we consider a nonlinear system. In the previous, we consider a linear system, and in the second, the nonlinear system. Now, in a nonlinear system, sometimes most of the cases we are unable to determine the flow operator or solution. In this case, we consider the linear approximation. And we always consider a linear approximation around the equilibrium point. And the equilibrium point by considering Taylor series expansion. Now, Taylor series expansion around the equilibrium points and or local linear approximation, then we get xi dot equal to d f of x naught xi. That means if we consider xi equal to x minus x naught. Now see here the advantage of the equilibrium point. That means f of x naught is the equilibrium point, then we have f of x naught equal to 0. Then xi dot equal to d f of x naught xi, and we neglect the higher order. Then we get the linear approximation. Therefore, when we consider the linear approximation, then naturally question arises, if we consider any equilibrium point linear approximation and we get the linear behavior, and this type of behavior is same behavior with the original frame of reference, that is nonlinear frame of reference. For this, we first define the equilibrium point. That means a equilibrium point is called a hyperbolic equilibrium point if none of the eigenvalues of the linear df of 0 have negative real part. That means eigenvalues are different from 0, then it is called hyperbolic equilibrium point. Now, I have already told you the sourcing and settle, etc. Now, Hartman-Goldman theorem says that when we consider a nonlinear system and we consider a linear approximation around the equilibrium point, if the equilibrium point is a hyperbolic equilibrium point, then two frame of reference, one of the linear frame of reference, another nonlinear frame of reference, they are topologically equivalent or typically same qualitative structure or behavior. Next, we define the invariant set. Now, E be an open subset of R to the power n, and we consider F belongs to C1E. When we consider F belongs to C1E, this implies that the solution of the system exists as well as E. And the solution is represented in the nonlinear frame of reference is phi t. And if S is a subset of E, this set is said to be invariant with respect to the flow phi t if the solution starts with the set S is always contained in the set S, then it is called invariant. And it is called positively invariant if this relation is satisfied only for positive value, and it is called negatively invariant if it is satisfied only for negative value of t. Now, stable manifold theorem. That means, see here, when we consider the linear approximation, then some of the eigenvalues are positive real part, some of the eigenvalues are negative real part. Therefore, let E be an open subset of R to the power n containing the origin, and F belongs to C1E, and phi t be the flow of the nonlinear system. And we consider f of 0 equal to 0. F of 0 equal to 0 means 0 is nothing but 0 is an eigenvalue of the nonlinear frame of reference. And df of 0 has k eigenvalues with negative real part, and remaining n minus k eigenvalues are positive real part. Then there exists a k-dimensional differential manifold S tangent to the stable subspace Es of the linear system 2 at the point 0. That means the equilibrium point 0. And obviously this set again invariant, and as t tends to infinity, since x0 is an stable equilibrium point, then at t tends to infinity, it should be equal to 0. Because eigenvalues are negative, then a stable behavior and obviously tends to 0. But n minus k eigenvalues are positive real part. That means unstable behavior. Therefore, if t tends to negative infinity, it should be equal to 0. Now, the Hartman-Goldman theorem. Hartman and Gorman, they are independently establish the relation in between these two. That means if phi t is the solution of the nonlinear frame of reference, and we know that the linear frame of reference, this is equal to e to the power at. And they are independently work on it. In 1960, Hartman 1960 they established, and in 1959 Gorman. That means they are the same things. Now they say that if E be an open subset of R to the power n containing the point x naught belongs to R to the power n, and F belongs to C to E, and phi t be the flow of the system. Again, we consider x0 equal to 0. That means x0 is nothing but x0 is the equilibrium point of the nonlinear frame of reference. That means this is your say nonlinear frame of reference, another is the linear frame of reference. Nonlinear frame of reference is the equilibrium points x naught, and obviously linear frame of reference should be converted to equilibrium point 0. And we know that the nonlinear frame of reference, the solution cannot determine explicitly, but we can say phi t is the solution because it satisfies the differential equation, nonlinear differential equation. Whereas in the linear frame of reference, and we can get the solution in the form e to the power 8. And there exists a homeomorphism in between these two frame of reference. This is called H. And this homeomorphism is also inverse continuous. That means H inverse also continuous. That means C1 diffeomorphism. And then we get H composition of phi tx is equal to e to the power at of hx. This relation, as well as the trajectory should be preserve the orientation of the y type. Orientation means, see here, in the nonlinear frame of reference, this is your linear frame of reference. If t1 in the nonlinear frame of reference, time t1 tends to time t2, then linear frame of reference h t1 should be tends to h t2. Again, when the trajectory starts from t1 to t2 in the nonlinear frame of reference, if it is a clockwise direction, then in the linear frame of reference, it should be a clockwise direction. That means it preserves the orientation of time. Now, we, in the linear frame of reference, the solution is sometimes very easy to determine the solution. If it is a coupled system, then we take the advantage of the linear algebra. Then we can get the decoupled system, and we can get easily solution by the converse proposition. That means we get the solution. Almost we get the solution of the linear frame of reference. But in the nonlinear frame of reference, we are unable to determine the solution explicitly. Now we check this property by considering a coupled system as well as decoupled system. Now this is your coupled system, x dot equal to ax. And we know the solution e to the power at x naught, if we passing through the initial value x0. Next, we consider the homeomorphism hs is equal to rx, where r equal to this and we r inverse of this. Then we taking the transformation y equal to hx is equal to rx. That means we taking y equal to rx. That means see here, when we convert the linear coupled linear system to a decoupled linear system, we consider y equal to p inverse x. In this case, is nothing but p equal to here. That means we consider this type of homeomorphism. Then we get y dot equal to this one, and that means coupled system converted to a decoupled system. And finally, we get this one. That means this theorem is satisfied. And if we see the trajectory, in the see here, in this trajectory in the coupled linear system, and obviously here two eigenvalues are real as well as opposite sign, that means the saddle behavior, and again we get the saddle behavior. There is nothing but if we rotate in the 45-degree rotation, then we get this type of behavior. Therefore, the Hartman-Gorman theorem is satisfied for this particular problem. Now, it is sometimes very difficult when we trace the behavior of the equilibrium point when the equilibrium point is not a hyperbolic equilibrium point. Because if it is a hyperbolic equilibrium point, then we consider linear approximation, and then we get the behavior of the linear frame of reference. They are topologically or quantitatively equivalent in the nonlinear frame of reference. But if the equilibrium point is not a hyperbolic equilibrium point, then we are unable to determine the behavior of the nonlinear system by considering the linear approximation. In this case, we consider the another stability is called Lyapunov stability, because Lyapunov construct it. Now we consider that the nonlinear system x dot equal to f of x. And the first assumption here, we consider the equilibrium point. The equilibrium point should be an isolated equilibrium point. That means containing the equilibrium point, there is some open domain in which there is no another equilibrium point. Next, we define the positive attractor. Now, the equilibrium point n star of the nonlinear system is called positive attractor if there exists a neighborhood around the point n star such that if we consider the n at initial time t, then obviously it belongs to this domain, and finally as t tends to infinity, it should be goes to n star. And if it is a negative as t tends to infinity, if this property is satisfied, then it's called negative attractor. Next, an equilibrium point n star is said to be Lyapunov stable if we choose any epsilon theta 0. There exists a delta depend on epsilon such that this relation is satisfied. That means if we choose the initial point around the equilibrium point, if the difference between these, the non-quantity is less than delta, then we get this. Then we can say that it is Lyapunov stable. Now, the asymptotically stable. The asymptotically stable, that means that t tends to infinity, this should be equal to 0. That means there is a asymptotic stability and Lyapunov stability. In difference in between these, we can compare with simple say limit and continuity. That means we can say that the limit is nothing but in the Lyapunov stability sense, whereas the continuity is the asymptotic stability behavior like that. Now, when n star is stable, stable means in the sense of Lyapunov stable, but not asymptotically stable, then we can say that the equilibrium point is neutrally stable. Stable. Next, see here, we consider the basin of attraction. Now, basin of attraction around the equilibrium point is defined by b n star equal to x belongs to r to the power n, such that limit t tends to infinity, this is equal to 0. And this is called a domain or basin of attraction. Therefore, if the domain or basin of attraction is r to the power n, then the equilibrium point, behavior of the equilibrium point is said to be globally asymptotically stable. That means if we start anywhere, then we can reach the equilibrium point, and it is called globally stable. Okay. Now we consider the method of Lyapunov method. Now, if in a Lyapunov method, first we consider say x dot equal to fx, then x naught is an isolated equilibrium point. Then we deconstruct a positive definite function. Let E be an open subset of r to the power n containing the equilibrium point x0, and a continuously differentiable real valued function is defined by v is mapping from E to R, is said to be positively defined if Vx greater than 0 for all x belongs to E minus the equilibrium point, and the value of the equilibrium point, this is equal to 0. Then it is called positive definite function. Similarly, if it is negative, then it is called negative definite function. Next, we define the derivative of v dot x, and v dot x is nothing but derivative. That means we take the directional derivative along the solution of the nonlinear system phi dot along the solution of phi tx, and v dot x is defined by this one. then if V dot x is strictly negative, then the equilibrium point is said to be stable. Stable means in the sense of Lyapunov stable. When V dot x less than equal to 0, then Lyapunov stable. When strictly negative, then it is called asymptotically stable. And when V dot x positive, then it is called unstable. Therefore, if the function, if satisfied the above hypothesis, then this function is called the Lyapunov function. Now, there is a question arise how to construct the Lyapunov function. Now we consider for simple problems like this one, x1 dot equal to x2 cube and x2 dot equal to x1 cube. This is a nonlinear, two-dimensional nonlinear system. And obviously df of 0 equal to 0. Here in this frame of reference, 0, 0 is an equilibrium point of the system. Equilibrium point of the system. Now see here, that means first we check that this equilibrium point is hyperbolic or non-hyperbolic. If this equilibrium point is hyperbolic, then the linear approximation, the behavior of the nonlinear system can be approximated by the linear approximation. But if it is not, the equilibrium point is not a hyperbolic equilibrium point, then we take the other method like say Lyapunov method. Now, if we easily check that the two eigenvalues are not different from 0, therefore this is the non-hyperbolic equilibrium point is a non-hyperbolic equilibrium point. If it is a non-hyperbolic equilibrium point, then we construct the Lyapunov function. Now, if we consider the Lyapunov function, say v equal to say x1 plus x2, and if we x1 square plus x2 first we assume this one. Therefore, if x1, x2 belongs to any coordinate, then obviously v is the positive definite function. Next, v0, that means equilibrium is v0 equal to 0. Therefore, the construction of the Lyapunov function is satisfied. That means v should be a positive definite function as well as the equilibrium point, this is equal to 0. Now, if we calculate the derivative of v, and then we have x1 dot plus x2, 2 into x1 dot plus 2 into x2 dot. And putting these values, then we are unable to determine the nature. It may be sometimes positive, it may be sometimes negative in the all quadrant. Therefore, construction is true, but this construction does not grant the nature of the equilibrium point. Similarly, in the if we try trial and error method, and we can get finally, if we choose this one, x1 to the power 4 plus x to the power 4, this type of Lyapunov function, then we easily observe that v0 equal to 0, and it is again positive definite function. And if we calculate the derivative of this one, then we have this is equal to 0. That means this property is satisfied. That means the equilibrium point is stable in the sense of Lyapunov is stable, but not asymptotically stable. And this is another problem on three-dimensional nonlinear frame of reference. And obviously, 0 is the equilibrium point, 0 in R cube, equilibrium point of the system. And two eigenvalues, see here, one of the eigenvalue, this is equal to 0. That the equilibrium point 0 is not a hyperbolic equilibrium point, the non-hyperbolic equilibrium point. And in this case, if we consider the Lyapunov function like this, and after some algebraic calculation, and we can easily check that, see that if we choose this one, then obviously positive definite function. That means we restrict on C1, C2, C3, all are positive. Then we get that v dot equal to 0. That means this is stable, but not asymptotically stable. Now, if we consider simple biological problem where SIR system, then we observe that here S plus I plus order, this is equal to 0. That means three-dimensional frame of reference can be reduced to a two-dimensional frame of reference. And this is the local linear approximation. Whereas if we consider simple preparator model in this form, and the equilibrium point, one of the equilibrium interior equilibrium point is, and this interior equilibrium point, the eigenvalues are purely imaginary. Therefore, we are unable to determine the nature of the nonlinear system by considering the linear approximation. In this case, we apply the Lyapunov method and we construct the Lyapunov function, this one, and we check it, it is converse or not. Now, all these are the references. Thank you. Is there any question?
Good morning, sir.
Good morning.
Sir, in the last slide,
Okay.
sir, how you take Lyapunov function in simple prep?
It is very difficult to construct the Lyapunov function, but Lyapunov, they can give the outline of the construction. This is nothing but this construction, like in the form, say, if we consider A star, I star, P star, any equilibrium point, obviously ending equilibrium point, the Lyapunov function construction is S minus S star minus S star log of S by S star, and similar things for others. And sometimes we consider some positive constants as C1, C2, C3, C1 into something plus C2 into something plus C3 into something, and this is the Lyapunov function. We know the definition of the Lyapunov function, but construction is not so easy.
Yes, sir, it's so difficult.
So difficult.
Yes, sir. Okay, sir. Thank you, sir.
Any question, please?
Can I stop my presentation?
Yes. Any question, please? Hello? I think there is no question.
Thank you. Thanks a lot.
Okay. Thank you, Dr. Bishas, for your valuable lecture.
Okay.
Okay. Thank you, Dr. Bishas. Our next speaker is Dr. Hirok Chaudhary. Sir, are you present here?
Yeah, I'm here.
Okay. Dr. Chaudhary is an associate professor, Department of Physics, NIT Durgapur. I request, sir, please deliver your lecture.
Yeah, thank you so much. So good morning, everyone. Let me share my screen. I would like to thank Dr. Krishnapada Das and the team for inviting me in this online platform to share our ideas on this topic. Could you please see the screen? Are you able to see the screen? The PPT?
Yes, sir. Yes, sir.
Yeah, that's very good. Thank you. Yeah, today I will have a talk on the investigation of the ECG signal using empirical mode decomposition technique. So here I will try to make you understand what is actually EMD, the empirical mode decomposition, how we can perform this EMD analysis, and how it could be helpful in different branch of science and technology, mainly application oriented, when you have a complex type of signal. That is our main target. So ECG, all of us know, all of us are familiar with the ECGs. These days, cardiac problem is a serious problem throughout the globe. So ECG signals are, conventional and well-established tool for any cardiologist to monitor about the heart situation, the condition that your heart is, how much it is in the trouble or it is in the good situation. And the most interesting thing is it is very easy and cost effective. That's why most of the cardiologists, they prefer the ECGs. But these days there are a lot of varieties also to know about details about the hearts, but those are very costly. So that's why we particularly focus on the ECG signal, so we can handle the whole scenario in a cost-effective manner. So this is a normal ECG signal that we can see when we have a electrocardiogram of our heart, or we can have this kind of pattern in an ECG graphical plot. Basically, it's a stochastic nature of the human heart, which is a complex kind of biological system, and it is a nonlinear and non-stationary signal. So how to get information from these nonlinear or non-stationary signals, that we are going to learn today. As I mentioned that there are many techniques. Here I have piled up the 10 medical tests which are very familiar and well known. That is the ECG, CTMT, angiogram, then CT coronary angiogram, Holter test, Doppler test, and normal the blood test also. So among all these, ECG is very cost effective. It is in the low cost. You can perform it, and you can have this in even in the rural area also. These days it is possible, but the other tests they are costly, and you have to go to a good hospitals where you have a lot of facilities. There only it is possible. Otherwise, you have to depend on the ECG signal to know about your heart scenario. And in country like India, developing countries, we know we have a serious problem with our health cover system. Though it's a very good in my opinion, but still, due to the lot of populations, we have to wait in a long queue. So we need a quick analysis of our heart. If you have a cardiac problem, then you can go for the ECG. And if you know in a proper way how to understand the ECG signal, that is normally done by medical practitioner. But if the physicists, the computational people, if they contribute here in a different way to know different nonlinear kind of impression in your cardiac system, then it will be good for any medical practitioner, any doctor, to know about your heart only through the ECG signals, and they can have a quick decision to if we need a surgery or not, or what kind of medicine they need to prescribe. So this is the situation. So here we have targeted a thing that is called the heart arrhythmia. That's a very well-known disease, and you can find it in many people. That is nothing but that kind of anxiety, palpitation of the heart, and also some breathlessness problem we feel during this arrhythmia disease. So it is associated with the onset of the other severe complication. You can go through a stroke and heart failure also. So if you take the ECG signal of a normal heart, it looks like this. That's just a cartoon. And if you take a patient arrhythmia patient, their ECG, it looks like this. So we'll go in detail about this. But how do you perform this? We are going to impose the empirical mode decomposition technique on the ECG signal to decompose your ECG data. Here, as an example, we have taken 64 ECG signal of the arrhythmia patient, and also for the normal people, to compare the scenario that we have gathered from the MIT VIH database. It's an open source kind of thing. Then we will make a intrinsic mode function, IMF function, that we are going to develop using the empirical mode decomposition from your original signal. Then we can analyze the whole scenario. That will be the overall lecture in today's this time slot. First, we'll learn how to do this EMD process. So let's see what is actually EMD. EMD is empirical mode decomposition. It's a nonlinear analysis tool for any complex, especially for a non-stationary time series data. In 1998, almost 30 years back, Dr. Wang actually developed this idea, working on a project in NASA, US, and Goddard Space Laboratory, and that make a revolution in that time. It was mainly working on they were mainly working on the hydrological system and the atmospheric system. But now these days, this kind of develop of nonlinear kind of theory and experimental process, now they are applying it for the biological system, and it looks like very effective for the biological system. So it is commonly referred to as empirical mode decomposition, as I mentioned, and if combined with a Hilbert spectral analysis, then it is called a Hilbert-Wang transform. Here is the picture of Professor Wang. As I mentioned, they were working in the NASA lab. This is the original paper and a highly cited paper, almost 30,000 citation it's got. This is the original paper, and here Dr. Huang actually used the idea of a German mathematician, Hilbert. He used the idea of the Hilbert spectrum and Hilbert space, then put some idea on his decomposition technique in Hilbert spectrum, and combinedly he named it as a Hilbert-Wang transform that we are going to learn today. So it is adaptively and locally decompose any non-stationary time series in a sum of intrinsic mode, as I mentioned. We'll also learn what is the intrinsic mode. Actually, this intrinsic mode represents a zero mean amplitude and frequency modulated components. You can also have the amplitude modulated components also. So it's basically oscillation embedded in the data system. The EMD represents a fully data-driven, it's a unsupervised kind of thing, automated kind of thing, signal decomposition, and does not need any priori defined basis system. That is the beauty of this analysis, that you don't need any priori defined basis system. And you can have it in a energy time kind of thing, in a reference frame, you can do this. So EMD also satisfies the perfect reconstruction property, that is superimposing all extracted IMS together with the residual slow train reconstruct that original signal without information loss. That is also a advantage of the system, and there will be no question of distortion of your signal. So let me make you understand how it works. Suppose you have a signal like this, and basically you have a fast oscillation superimposed to a slow oscillation, or it could be vice versa. That is, you have a slow oscillation and one fast oscillation is going to superimpose on that. So that then you can have an idea of the EMD on that signal to consider the oscillatory signal at the level of their local oscillation. So this local oscillation is a very important term here to formalize the whole idea. So you have this original signal. It looks like this for say just it looks like this for the time being. You can consider this amplitude with time variation. This happening. That's a time series data. Now what we can do? We can have an upper envelope and lower envelope of the data. This is the upper envelope. You can see that draws the upper envelope, and here you can see the lower envelope. So we need to reconstruct a upper envelope and lower envelope from the original data, and also having a mean that we are called a zero mean. So basically you have the data, you have the upper envelope, you have the lower envelope, and you have a mean data that we need to construct mathematically, and so some software, any kind of software that you can use the Origin, you can use the MATLAB, you can use the Python, in any platform, open source platform also you can do, no problem. And then you need to put a shifting process. Now the question is, why shifting process? I am coming to that part. So after shifting process, you can see your data looks like this, and from there you can develop the intrinsic mode at every situation, what is happening in your non-stationary data, that now you can monitor, you can analyze. That is the beauty of the IMF, each IMF that you can build from your original signal. So the EMD algorithm thus considers a signal oscillation at a very local level and separates the data into locally non-overlapping timescale components. So what is your IMF? What is your intrinsic mode function? How we can build it? So an IMF has only one extremum between two subsequent zero crossing. That is, the number of local minima and maxima differs at most by one. So that is basically the idea of the adaptation of the narrowband concept, that you are putting a narrowband concept in your data set. And secondly, then IMF has a mean value of 0, as I mentioned. That is, the mean values basically for the upper envelope and for the lower envelope, which correspond to your local maxima and local minima. So that's basically you want to keep a symmetry, local symmetry property in your data set. That is the idea. So how to find this, how to define this? So the process is called the shifting process. Sorry, one H will be here. Through shifting process, you can make this. What kind of shifting and how you can perform this? So number one, identify all extrema in your data set, all your maxima, minima. Suppose your data set is you are defining it with xt. Then interpolate the local maxima to form an upper envelope. Suppose this is ux. Then again interpolate the local minima to form the lower envelope, and you can nomenclature it as Lx like this. Then calculate the mean envelope that you are defining like this way you are defining this. Then extract the mean from the signal. So every time we have to extract the mean from the signal. So HT, that is the this way you are defining this original signal minus your mean value. And you have to follow a process, a algorithm to find your first IMF. You can have a number of IMF in your data set as you are extracting, but you need to know where to stop this process, that iteration process, where you have to stop this interpolating all these things. So the idea is like that if HT is an IMF, then you got that proper IMF, then you can stop the shifting process. If it is yes, and if it is you don't require this, then you can you have to again follow that same path that keep shifting is going on. With this pictorial representation, you can understand in a better way. This is the original signal. Suppose we have the signal like a ramp or triangular wave, and you can build your first IMF like this. That is the high frequency triangular waveform you have, which is slowly growing. And then in the first IMF, you can have a middle frequency sine wave like this, which have a quickly decaying kind of thing. And you have a low frequency triangular waveform like this. And from there, you can build different kind of IMF. And we are putting their name like IMF 1, IMF 2, IMF 3. And you can go for n number of IMFs, theoretically, no problem. But as I mentioned, that you need to stop that process of shifting. So there, what will happen? After a while, you will get a, you don't require the shifting. Then you can name all the rest of the IMFs as the residue. So your residue will look like this. And now we are going to work with each of the IMF. We are going to explore each of the IMF in a energy time kind of plot. So you have to keep in mind that second condition, that is, as I mentioned, that local symmetry you have to keep in the data system. So the second condition implies that an IMF is a stationary, which simplifies the analysis. But an IMF may have amplitude modulation and also changing frequency. I also mentioned that term before. So here we are going to now apply the Hilbert transformation in the Hilbert space on the Hilbert spectrum. We are going to do that. So here we have to follow some criteria. What are the criteria? That is, it should be nearly orthogonal, it should be local, and it should be highly adaptive and complete by employing stopping criteria. So you have to fix the stopping criteria. So altogether, in a short way, you can name it as cola, not the Coca-Cola. It's just cola. So that is the complete, then orthogonal, then local, and the adaptive. This cola formula you have to fix up when you are developing this. That was the idea put by Wang, taking the idea of the Hilbert, and togetherly now it is known as Hilbert-Wang transform. So this cartoon can make you understand what we are actually trying to do. So suppose this is your original signal, and from there you are having a mean, and you are having an upper envelope, you are having a lower envelope, and here is these are your upper envelope, lower envelope, and from there you are developing your IMF, intrinsic mode function. So your first IMF you are developing like this, your original signal minus your mean value. Then IMF2, IMF3, and so on you can develop. And on the residual part, you can have the original signal minus the last IMF what you have developed. For here, this is IMF1. So original signal minus IMF1, or the original signal, or you can put IMF10th or IMF12th, IMF21st, whatever you like, but it's based on your shifting process that you need to understand. The problem and the issue is here that no clear-cut theoretical perspective is still there that where to stop. That is the lacuna in this kind of analysis, but that analysis is very good in that sense. So here you have the source data. If you try to understand the flowchart, you can have this like this way. You have the source data, then you are doing the shifting process, and from there you are getting the intrinsic mode functions, then a trained or constant, then you are putting the Hilbert transform, you are having the Hilbert spectrum and time integral of all this, you are getting the marginal spectrum, and you can have the analysis. And if you are following this from here, if it is yes, you can go like this way. If it is no, again you have to do the shifting process. That is the idea. So this is the simple flowchart that you find the local maxima and minima, then compute the interpolating signals that you develop the envelopes, the upper envelope and lower envelope, compute the mean value like this, then subtract from the original signal all this mean value, what you develop. Then if satisfy the stopping criteria, then you can go for, okay, you can go for this way. That is, this is the algorithm 1. You are developing the IMF, and from there you can, monotonic kind of thing. Then you will have this. And you will convert it in a Hilbert transform, you will put in a Hilbert transform, and Hilbert spectrum you can find. And if it is not, again you go for the shifting process. And if it is not satisfied the stopping criteria, again you have to start from the beginning. That is, you have to develop all the different kind of IMFs this way. People have explained this and they have checked it. With Lina, I'm just giving the example. This is the original picture, and from the original picture, suppose you have the IMF1 or mode 1. Mode means the IMF. Then mode 1, mode 2, IMF2, IMF3, IMF4, IMF5, IMF6, IMF7, IMF8. This way you are decomposing your original signal. And finally, you are getting a residue up to IMF9. Here we have gone and we have find a residue. And from there, again, you want to reconstruct the signal. So what the advantage in between whatever IMF you are getting, now you can analyze them in a beautiful way, in an elegant manner. That is the beauty of the entire subject. And here you see the original picture and some of the IMF are same. So you are not going to lose any data. There is no chance of the losing any data or distortion of kind of thing. That's why these days people are applying, scientists are applying this EMD analysis in different kind of thing, in nonlinear wave evolution, climate kind of thing, earthquake engineering, submarine design, structural damage detection in a building block, in satellite data analysis, turbulence flow, in the medical science also in the non-destructive testing, health monitoring, economic data analysis, the financial data analysis, to understand the complex brain signals and a different kind of perspective. People are now these days applying this EMD technique. So for a case study, we have taken, as I mentioned, the arrhythmia patient ECG signal and normal people ECG also, and we have compared them after applying the EMD, empirical mode decomposition. That I am going to explore now. What way we are doing. The idea is very simple. We have collected the data. It's a huge data sets. Then we have pre-processed the data using some filter to remove some noise in the signal. We have used the SG filter. We have developed all the IMFs, intrinsic mode functions of both the patient and the normal people. For both cases, we have developed this. Then we have processed the data using the concept of the Hurst exponent. I will come to that Hurst exponent also. And we have statistically checked this. And we have also checked all the IMFs. Then we have analyzed the data in a pattern recognition form and calculate both the linear and non-linear parameter. And we have also subgroup all the data in terms of both the male and female scenario, what is happening in male and female in case of their heart disease, and also in terms of different age. We have taken different age group of people, and what is happening in the age group. We try to understand the arrhythmia disease in different age group, both in male and female. Also, what is happening in our normal heart signal for both female and male in different age group, that we are trying to explore. So we have taken the data from the PhysioNet. That's an open data source for medical science. You can get the data free of cost here. We have taken it from the MIT VIH arrhythmia database. That is also open source kind of thing. You can have the data from there. Then what we have done, we have taken the full length ECG time series data for 48 arrhythmia patients. That was taken from the MIT VIH data set. Then patients were 25 men and aged between 32 to 89, and 22 women for age between 23 to 89 years. Then record of different kind of patient data. We have named them, tagged them like different kind of patient, like 201, 202. These are the tag we have put in that kind of thing. We have also taken the normal, people ECG signal from the same database, and we have compared them as I mentioned. And in between, we have put the SG filter, and we use some MATLAB coding, and we done the whole thing in a MATLAB and also in the Origin software. So how we are putting this this filtering process, this SG filter, that for our case we have employed different kind of thing. That is the please have a seat. For different kind of thing, that suppose we have taken the period of time period of the ECG signal for disease and normal people like this, and length of the data that you can see, it's a huge number of data, not so huge that sense. And we put a frame of SG filter 37. You can change as per your choice, no problem. Order of SG filter, we put 3 here for both the normal and the disease data set. And we try to calculate the Hurst exponent out of this using R by S technique. So here is your normal data, ECG data of a normal person that we have taken from there. And this is a data of the disease person that you can see here. Now we are trying to explore using the EMD. So what we have done, we have developed the IMF using the EMD, empirical mode decomposition. So this is our first IMF for a patient data set. We have done the same thing for the normal people data set. So we developed IMF1, IMF2, IMF3, and so on up to IMF12. And then we also done for the residue. And then in all these IMF, we are trying to identify what is happening in terms of the Hurst exponent on nonlinearity of the system, in the non-stationarity of the system. So here you can understand, suppose for the patient ID 19090, that is a particular patient. It's a normal, not the patient that says, it's a normal person, it's heart condition. We have taken different IMF for that, and we have calculated the Hurst exponent for all these IMF. Similar way, we have also taken the patient number 100, disease data, ECG data, and we have calculated the Hurst exponent for all these IMFs. Let's see what is the scenario in the Hurst exponent. But before going to that, we need to understand the Hurst exponent. Hurst exponent, you know that that is a nonlinear feature of a system that will tell you about your data set scenario. You can have it both for stationary kind of data set and a non-stationary kind of data sets. If it's a non-stationary kind of data set, then Hurst exponent you can explore like this, alpha minus 1. And if it's for stationary, it is just similar like your alpha. Alpha and beta is normal exponent that we normally do in any kind of time series analysis where you have where it is following the power law kind of thing. And if you have a if you try to find out the beta exponent from that, that is the normal relation. And using the beta, you can also have the Hurst exponent like this way for stationary and non-stationary data. But you have to fulfill this criteria. You have to follow this criteria. Your beta falls under this, should falls under this for stationary and non-stationary data. So basically, the Hurst exponent, its discovery was very interesting. It's long back when people were trying to develop some reservoir in the river Nile in the Egypt. So one hydrologist came with an idea of Hurst exponent. So every year the Egypt government put a lot of money on that. But unfortunately, after putting money to develop a big reservoir on the Nile River, so in every monsoon, every rain season, everything was flushed out. That was happening, and government was just frustrated what is happening. Then this hydrologist Professor Hurst came with that and came with an exponent after nonlinear analysis of this, and he put that what could be the solution to develop a big reservoir on the river Nile. First, we need a theoretical model, and then we can go for the architect and civil engineering. Rest of the part we can do. From that time, on honor of his name, this exponent has been named. And that is a fantastic tool for any time series analysis or nonlinear analysis. In our previous talk, we see that professor was talking about the Lyapunov exponent. That is also a good tool. Just like this Lyapunov exponent, Hurst exponent is another kind of exponent that we can have. So if your Hurst exponent is in between 0 to 0.5, you can find an anti-correlation in your data set. If it is in between 0.5 to 1, that's you can have a long-range correlation. If it is just 0, that demonstrates the pink noise or white noise in your system data set. If it is 0.5, it means random. And if it is 1, you can have a self-similar process. That is interesting. That's explored another branch of physics, that is the self-organized criticality. Many physical systems follow this self-organized criticality, where your Hurst exponent, if nearly to 1, then you can think about that. Many processes, just like I'm giving an example, earthquakes. So the entire subject is very much interesting. Earthquake is follow a self-similar kind of process. SOC behavior you can find. Even in the stock exchange data, you can find this kind of thing. So Hurst exponent is a fundamental tool to understand all this. So what we did, we took the arrhythmia patient data set, ECG data set, and normal people ECG data set. We put the EMD, empirical mode decomposition on that. We put there. Then we analyze all the intrinsic mode function. We develop that. And in each IMF, we have what we have done. We have calculated the Hurst exponent, and we try to figure out what is the nonlinearity in the system. So basically, Hurst exponent is referred as an index of long range dependence on the system. So the Hurst exponent is used as a measure of long-term memory in a situation. Here you can see now what we have done. We have taken the normal data and disease data. Here with the patient ID or for the different patient we have taken, as I mentioned, that we have taken almost 48 data set to understand this scenario. And for each case, we have calculated the Hurst exponent both for the normal data and patient data. And we have plotted them in a age-wise manner. We have also done this. In a different age, we have taken different people, as I mentioned, starting from age of 32 to 89 in case of female, and 21 to 87 in case of male. We have taken this age limit both for the normal people data and the arrhythmia heart disease data also. And we have calculated mean, mode, and the p-value, and also the age value, the Hurst exponent for this. And here with the R by S technique, we have calculated the Hurst exponent. There are another two techniques to calculate the Hurst exponent also, but here we have applied the R by S technique. I'm not going to the detail of this R by S technique due to the lack of time. We need a separate class to make you understand about this. I think many of you know also about this. So this way we have calculated the Hurst exponent, and that varies from 0.969 like this. Even it goes to high value like 1.03 1.0148 like this. For the residue of the IMF, for the IMF1, IMF2, for every IMF we have calculated the Hurst exponent. So a distinct difference between these Hurst exponent values of the first IMF, which is the most important IMF in our case, between the normal individuals and arrhythmia affected patient was identified. So this observation was further validated through an age-based and a gender-based analysis. That is what is happening in case of male, what is happening in case of female, which was demonstrated a unique alteration pattern with age. Now we are coming to that data sheet with what is happening with age. Here we have taken of a age bar that we have taken where the patient or the normal people whose age is less than 30 years. That is very young people. And who are in the middle age, we have taken the data for them else. Also that is the 30 to 50 years age, the middle age people. Actually, this heart disease normally these days we know it's starting to come after age of 35, 40. Different kind of things are coming, and when you have obviously you are so senior, above 50 or 60 or 70. In many cases, we have a lot of heart disease we are observing these days. So this way, we have taken different age limit, and we have calculated the Hurst exponent on different aged people, both for male and female, for normal people and for the disease people. So this is the scenario in this plot. You can see here we have see the Hurst exponent changes, what is happening in case of male and female, in case of normal people and disease people in general, and what is happening in terms of different age group. That is, if age is less than 30, what is the happening in Hurst exponent, and how much it can, how much changes it can happen there. That we have also checked. And what is happening in the middle-aged people, and what is happening in the case of the senior people, the senior citizens, that we have also checked. So that way we have figured out all these things. And we also made a scatter plot along with the confidence ellipse for the first EMFs, mainly for the Hurst exponent, what we have calculated. So this is the scenario where you can see for the normal data and the disease data with the this kind of R values we are getting like this. So quickly we can conclude that this EMD technique was performed on the nonlinear and non-stationary ECG signal to diagnose cardiovascular disease. Mainly we have targeted the arrhythmia diseases. The EMFs, which are the fundamentally decomposed signal of a whole ECG signal, were extracted for arrhythmia arrested patients and also for the normal subject using the EMD technique. So a comparative study based on the enumerated age of the IMF was carried out to to distinguish the arrhythmia patient from the normal people. So in this analysis, a distinct boundary between Hurst exponent values of normal and disease patient was encountered, which indicates that contrast in dynamics of the cardiac system between normal and disease individuals. We are getting changes. We are observing the changes. So if some doctor get this idea of the Hurst exponent, using some software, they are putting their ECG signal and they are getting the Hurst exponent of this and each of the IMF, so they can be sure what is happening in your cardiac system just using the ECG signal. I think they don't have to go for the different kind of Holter states, angioplasty, angiogram, the Doppler states, which are really very costly and not available in all cities or rural area. It is very you are getting in a sophisticated kind of hospitals these days. So the study shows that a probability of 94.92% was expected towards the predictability of arrhythmia disease in a patient. However, this analysis is restricted to the particular disease data set. So this kind of analysis incorporated with machine learning might bring about a transformation in the current scenario of the healthcare system, which is our next thought. We are trying to now put the idea of the machine learning on this all these data sets. So a systematic analysis could be carried out on other cardiovascular disease apart from the arrhythmia data set to ensure the predictability proportion. But here it is going to be, looks like very successful kind of thing, but we have to see what is happening in other kind of data sets, in a cardiac data set or even in the brain data set that one needs to check out. So moreover, the decision could be verified by means of applying other different nonlinear techniques that we are also doing. That is, we are putting the wave plate analysis, the multifractal analysis, even the self-organized criticality kind of analysis. We are also putting on that kind of thing. And also we are putting the MFDFF technique, multifactorial dependent fluctuation analysis. So this kind of analysis incorporated with the machine learning might bring about a transformation in the current scenario of the healthcare system. So quickly we can say adopting this EMD-based procedure for the ECG data analysis and disease prediction may assist in reducing our dependence on institution-based diagnosis of ECG reports by medical practitioners and may provide a novel insights into the functioning of the human heart, which might help develop new biomedical strategies to combat cardiac disorder. We are really thankful to my institute, the National Institute of Technology, for providing both the financial and institutional support for carrying out this research work. Apart from BST ACRB, we are also having this project, and we are thankful to our PhD students and master students who are helping us in this kind of development of this EMD analysis in our lab. If you are interested, you can have a quick look on this paper, which is still in the research in open source kind of thing, so that it can easily reach many people in a social science network. We have given it in so you can have it in a free of cost to get the idea. And if you are still more interested, you can go through this book. This is just an example that research advances in biomedical signal processing. There you can get the idea of the entire detail of the EMD process and how people are using the biomedical signal. So thank you all. Thank you for your time and your patience for listening me. Thanks.
Thank you, sir, for your valuable lectures. Is there any question, please?
Okay, if you don't have any question, no problem. This is my email ID. If someone wants to contact, they can contact me through this email, either this or this.
Thank you, sir, for your valuable lecture and time to give us.
Thank you. Thank you so much.
Okay, sir.
May I leave now?
Yes, sir. Okay.
Thank you. Thank you. Thank you. Bye-bye.
Thank you, sir. Okay. Our next lecturer is Dr. Gajendra Pratap Singh. Sir, I think you with us. Dr. Singh?
Yes, I'm here. Thank you very much, sir. Yes, I can.
Dr. Singh is an assistant professor of Jawaharlal Nehru University, Delhi. I request, sir, please deliver your lecture. Sir, your microphone is.
Yes, okay.
Okay.
I can hear your voice.
Okay, sir.
Thank you very much, Dr. Pradeep Roy and Dr. Krishna Panda, for inviting me and such a very nice gathering connected here in this online platform. And I have seen plenty of speakers showing their interest in diverse areas. So in this discussion, in this talk, actually, I will try to put some applications, sometimes real life and theoretical applications, also the theory, with the help of basically one tool is Petrinet. I will show here, and some at the end, if I got the time, I can show some demonstration with the help of some kind of software, our software Petrinet tool. I will try to show here. So for this, let me share the screen first in this platform. Anyone please confirm me whether the screen or not visible or not, so that I can have a broad idea about. I think this is visible. Two screens are visible. Anyone please confirm me. Is it fine? Two screens are visible. Is this fine?
Yes, sir, it is fine.
Oh, okay, fine. That is a talk basically, mathematical modeling using Petrinets and its application in diverse area. So just tell me, I just let me introduce, starting with some kind of introduction of Petrinet. Petrinet basically it is originate from the graph theory, and it is a one kind of a special graph. It is a directed bipartite graph, and it was discovered or given, that concept given by in 1962 by the Carl Adam Petri, German mathematician, and in 1962, basically 61, he has submitted he submitted that his thesis to Damas University, and 62 he has defended his viva. And after that, lot of work has been done, not only in mathematics but also in several plenty of area, diverse area, in bioinformatics, mathematics, computational biology, and computer science, social science, even several areas. Because this is it can be treated as a theoretical subject or area for the research, also the applied area, and also sometime if we have expertise in programming, it can also be seen as one kind of tool, basically tool, or that tool can be used to train the machine. It is a special kind of, also one kind of machine learning. We can train the machine. Fine. Here, generally, the application of the Petrinet used in model the complex system. Complex system, those system which cannot be studied directly, or it is very difficult to study. For example, biological system or computer science network. If we study, it is very difficult to start. But if we use the Petrinet concept, with this concept, we can get the idea how or where we should start the process. First of all, we can generate the all possible number of states with the help of this concept Petrinet. Let me scroll down my some kind of slides. These are basically how to start the work. Maybe several researchers the terminology heard first time. But this is the thing basically we can follow for our research. And the first article or first concept any researcher can see in this book, basically communication with automata. It can be original contest can be seen. It was in German basically, and English version also available right now. And after that, several variations has been done in the definition of the patinates. Several variations given considering the different background, diverse background or requirement, time to time requirement. They have changed the definitions, slightly changed, not all, modified the definition, Holt, Commoner, Patil, Pilskill, Jensen, Murata. But in this contest, in this discussion, I will use this definition, Jensen definition, because this is in the form of matrix. And I feel that matrix is more organized way or more operatic definition. Even the beginners can understand how to use the matrix form of the Jensen definition I'm using here. It is basically discrete driven dynamical system, because we have in this patinate we have some kind of conditions, events, and their dynamics that we will show in coming slides. Very visually I will try to show here. And why, as I told, because several systems are very complex. It is very difficult to study directly, but they can, for example, astronomy, sociology, computer science. So in those areas, but not limited, we can use the patinate. And other diverse application you can see here in this form. And basically this is the pictorial representation of the patinate. Pictorial means I design the PPT, not the mathematical point of view, but anyone can understand that you are using the pictorial notation. Whenever we have two kinds of elements. One is the boxes, that is the transitions. Transition means any actions in our modeling, any kind of activity, any kind of action in modeling can be taken, can be represented by the boxes. What we call is transitions. Any kind of stable thing, dummy thing in the modeling, if we have a static thing, we can take as a circle are called here place node or places. And the arrow means arrow connect the place node and transition. That means any dummy thing and the actionable thing, it can connect directed arc by that arrow, means maybe the inward or maybe the outgoing arc. And dot means that dot is called the marking, sometimes it's called token. Token means any place, because place is a dummy or stable thing, it can accommodate any number of token. Token means any kind of informations, any kind of resources, any kind of present that can be taken as a token or some kind, we call it a marking as well. We have these kind of elements, basically four kinds of elements: boxes, transition, and dot inside the places, and arrow. Okay, one action means transition, and dummy or stable things are the transition place nodes. So that is the definition. I can also explain whenever I will show how it works, the dynamics. I will explain here. So whenever means it is a 5 tuple basically, and trace means it is a set of elements basically. It is a basically directed bipartite graph. If anyone has the idea about the directed bipartite graph, means we have a set of vertices and connectivity between them. Set of vertices means we split the set of vertices into two disjoint subsets. Two disjoint subset. One set is called places, and second set is called the transitions. And just like if we split the set of vertices, means we are not allowing the connection within the subset. We are splitting the vertex set into two subsets, such that if we have any kind of connection, any kind of relation, can be the one end should be one subset, second should be the another set. We are not allowing the connection in between within the subset. Similarly, have place nodes and transition nodes, both are disjoint. And I minus I plus, basically these are the incident functions or negative function and positive. Negative means Negative means any number of arc from place to transition. That is a minus I minus the, function. Positive means any arc transition to place. That is the meaning of the I plus. And the fifth condition is show that every place has to be connected by a transition, or every transition has to be connected by a places. And mu naught is also function place node to the n, and I'm taking here a whole number, including basically natural number including 0. That is the initial marking whenever we have some kind of initial token in terms of token. And in addition to that, there are a lot of variation of what is the reason of the popularity of such kind of pertinent, because we have several kind of variations of the pertinence. Maybe the in terms of stochastic nature, stochastic pertinent we have, continuous pertinent, and we also has some other pertinent, hybrid pertinent, fuzzy pertinent. That is why it can be used in several areas. Here, this I'm discussing here only the simple kind of pertinent. So now, after that, let me show here that is a pictorial representation of the pertinent here. Here, I just wanted to explain some elements of the pertinent. We have the 3 places and the 4 transitions. And dot means P1 place has 3 dots. Means I can say mu naught P1. P1 has 3 tokens, 3 dots. Marking of the place P1 is 3. Similarly, P2 has 1. Marking P2 is 0 and P3 is 1. Marking vector is now we can visualize the information that place can hold in terms of marking vector. So here also now we are with the vector. So now we can also use the application of the linear algebra here as well in this in using the pertinent, right? And weight means that means 3 arcs, 2 arcs are there. Transition T1 to P2. 3 means 3 arcs are there. You can connect. You can put the 3 arcs, or you can write weight as well. That is also the one kind of notation. So here I'm leaving this one. That is one kind of interpretation of the places and time transition while we are doing modeling of any complex system or discrete event driven system. If we want to model any kind of event or computational step, process, task can be the transition. Input data, output signal, you can see, and condition buffer, it can be the input place, transition output place or transition input place. It can be. Other interpretations, places can be any kind of buffer, channel, geographical locations, condition, states, and transition can be the any kind of event, transformations, and the token represent the humans. Human means any kind of humans, number of humans, goods, any kind of articles, machines, it can be any kind of information that can be considered as the token, right? That is very important things here to see the dynamics or the internal behavior of the pertinent, right? And with the help of this, I will also show here how we can use such kind of thing in communicable diseases, for example, tuberculosis or other cardiovascular functions or diseases we can also do. So if n is any kind of pertinent, it is because it is a 5 tuples. And under that, because transition is the action, right? If transition is the action, then any transition T can be enabled at the marking mu. Okay. If and only if arcs from, because I minus means arc from place to transition is less than equal to number of marking or number of dots at this place mu P. If this condition is hold, then I can see that the transition is enabled. Okay. If the transition is enabled, then the enabled transition, only the enabled transition can fire. Okay. It is up to you. You can fire or not. If the event actually takes place, you can fire that transition. After firing, that means new state. If you want to find the new state, you can use this formula. This is a new updated marking or updated state of the system. Number of token at initially previous one. I minus means arc from transition to place to transition. I plus means arc from transition to place. We can use this equation and we can find the new state or updated or modified state of the system. by using the previous state. So that is very important thing. One is this enabling condition. Second is the new state or the updated state, right? So whenever we have condition or condition satisfied, that means condition is enabled. Okay, if the condition is not enabled, transition never fire. That is very important thing here. Okay, and enabled condition may or may not be fire. If the event actually take place, you can fire, otherwise you can stop. That is the beauty of the pattern. That flexibility is available is the pattern. For example, that is very smallest example here. Okay, so we have two places and here two conditions. It is given here. Some arcs are also connected here. What is the initial state of the system here? If I consider here, so what is the initial state is 2, 0, because place P1 has the two tokens. I can here it has 2 token and it has 0 token. What is the initial marking? If I say the initial marking of this kind of situation, it is a 2, 0, right? Initial state or initial marking. So at this stage, I will check here first whether the condition enabled or a condition T1 or T2 are enabled or not. How I can check this? I will use this condition, right? For example, T1, whether the transition T1 is enabled or not. So I can say here, I can check here, arc from place to transition is 1. I can write here 1. Number of token is 2 in this place. Arc is 1 and number of arc reverse transition to place I plus means that is 1. The marking is 2. Updated marking is 2. That means if transition T1 is fire, then marking in place P1 is remains unchanged. And what about the T2? T2 means if I use the T2 means the number of token is 0 initially. Arc from P2 to T1 is 0 and arc from T1 to P2 is 1. That means the token is 1. The new state of the system, whenever transition T1 is enabled, it becomes 202, is changed 202 to 1. Similarly, I can again check here whether the transition 2 or 1 at this state transitions are enabled or no. I can further check till the marking become dead generally. Okay. Also here T2 is also enabled. I can show here in the next slide. You can see here in this slide, right? So at this stage, if I fire T1, T2, if I fire T1, this is a new state of the system. If I fire T2, the new state is 0 and 1. If T2 fire, the new state has been changed here. Here, if I continue this process, I will be here. So now we can see here with the help of this, okay, very smallest graph. This we cannot do in ordinary graph theory. Graph theory, there is no dynamic internal behavior. We do not have the idea. But here we can get the idea about the internal nodes or intermediate states basically, right? So here, by using this one only, very small network we have the 6 possible number of states. Okay, so here this state is immediately reachable from this state, and this state is reachable after some successive states, right? And that means this state can be obtained after the 2 times firing of T1 and T2. I can write here that T1 and T2, this can be obtained, right? And this state can be obtained T1 and T2, the sequence T1, T2, and this is the final state. This is the final state after the firing of T1 and T2. Here we can see here, similarly after firing of this one. So we have the final state is this 0, 3, here 2, 2. So we have several states. Okay. So whenever we model that system with the help of PactiNet, so it is up to you, up to the decision maker. They can take the decision. They can start the system from here. They can start the process from here. They can start from the here. Okay, or they can start from here. Fine. So a lot of states has been changed. That is just an example. Fine. But there are also the situation in a real life problem. Whenever we have very small situation and there's no condition, there's no situation means the system, the state we will get that every time new state. Then the system is very live, not a terminating system. Okay, it is very difficult to stop. So we have a concept how we can stop. We can restrict the number of transition of the firing in some state where our process completed. That is also we have some kind of provision in this. Fine. So here, what kind of research question we can have? Suppose we are here, we want to this state, we can check that whether this state is reachable or not from the initial state, whether the situation arise or not. So we can use, so what will be the optimal number of transition firing? That kind of question we can have. Okay, in general questions. What are the minimum number of steps of firing? And what are the maximum number of steps? Or when the system become dead? Or at what state the system become infinitely go? Several property we can analyze. Or what are the maximum number of tokens? Or how many number of tokens? How many number of resources we can accommodate in a place? That, or we can say check, in other words, we can check the boundedness, because these are the very basic question in complex system. Okay, when it is stopped, when it is bounded, when it will be live, or what is the optimal sequence? Such kind of question we can have. So for this, we can have such kind of sequence. We can write the sequence. We can find the several number of sequence. Even more, several sequences are possible. We can choose the sequence of firing or sequence of actions, basically. Okay, of the sequence of the actions of the transition, of firing of the transition means optimal sequence we can choose. We can choose the optimal sequence that you can get, that can be run, that can be achieved with the minimum number of steps of the firing of the transitions. Right. So in this way, the same situation we can also express. I can show you here in terms of the tree. Actually, this is the factory. We have 4 places and 3 transitions. Okay, this can be obtained. This can be also obtained in terms of the reachable tree. So here, all transitions are enabled at this initial state to 111. I can see here. I'm using the same formula, same firing formula. I already explained you. Number of arc less than equal to mu p. That firing rule I'm using here, and T1, T2 fires, and at the last I can see here that is a dead marking, that low occurs here. Fine. So here several markings are available. So I can express the information, the resources in terms of the reachable tree. That is called the reachable tree. Okay, and there's no cycle. If there's a cycle is also possible in whenever you fire, we will get the same marking. That is also possible. So in that case, it is called the reachability graph, right? Because there is no cycle, I'm telling it is reachability graph. Right? So we can analysis, we can use the several property of the tree here, and several analysis we can do whenever we have the tree, reachable tree. Okay, and that means with this concept, if we are good in the programming languages, we can write own program and we can train the machine. That is one kind of supervised learning, or sometimes we can also train the machine as a unsupervised learning, or reinforced learning is also applicable here, if you know those basic concepts. Fine, I'm leaving this one. I just wanted to explain here how we can use those basic concept. I can express also matrix form. I'm not going into depth. Okay, so now how we can use those areas in modeling area of the pertinent in computer science. Okay, so that means whenever we have the sequential analysis or sequential executions, right? So in that case, whenever we model here in this way we have sequence or series analysis, if you want to see. Okay, here the initial marking is 0. One is here. All places have only 0 tokens. So whenever we fire the event E1, the token move by the firing rule from here to here. In the next step, you can see here that indicate that this is the running process. Okay, or I can say this event cannot fire unless this event is fire. That is sequence analysis. Whenever we in our real life situation, we have the sequence analysis, we can use such kind of sequence analysis. We can fit as it is in our modeling to analyze, or some kind of process sequence analysis. Okay. Similarly, at the last, the token is stored here. Suppose we have in our real life situation, the conflict situation or the choice or decision. Okay. So we can also use here. Now we can see here, this is a conflict situation. At this marking, if I check the firing rule or condition, at this marking, all place transition are enabled. Okay. So in this case, it is very difficult which transition we should, or which transition we should fire first. So here, what is the rule of this? Whenever if I fire the transition E1, all transition will disable automatically. Okay, if we have such kind of situation, right? If one is in rest machine, the system stop or not able to in working position, fine. The token will move from here to here. Suppose you want to fire this one, these are disabled, these are disabled. We can use the system has been changed, the state of the system has been changed. Similarly, we can fire the other E3 means T3 transitions. Same concept we can use in the concurrency. Concurrency means we can have at a time same task if the machine perform or several machine perform same task at the same time. Okay, so in that case we can fire all the at a time one, or we can fire one by one in the all transition in the firing. In the firing, we can fire all the transition. That is a concurrency situation. Whenever we fire, okay, maybe the single transition, maybe the whole transition at a time. This is the molding state. We can change, we can get the new updated state in this way. Same situation we can use here, synchronized situation. Whenever we have some kind of problem, synchronize. At this marking, if you check here, oh, this transition is enabled, fine. It doesn't mean that we have the before the firing we have number of one token, one token, one token. It doesn't mean that after firing you will have 3 tokens. It doesn't mean that. Okay, so that token, whenever transition are fired, that token will consume from the input places, that will deposit to the output places here. Okay, output places mean only the one token will deposit by using the firing rule here like this. Okay, now token is consumed, or dots are, or resources are consumed from the input places and deposit the output places, not the 3. Okay, that is the beauty. It doesn't mean that whatever number input places are there, that the accumulated token will be deposited here. It can be, but here this is a synchronization case. It never. That means we have synchronized our information into a one unit. That is the concept we can use. That is the power of. Similarly, we can model the mutually exclusive process problem. This pertinent that whenever loading and unloading, so at this stage, transition T1 and T3 both are enabled. At a time, if this is enabled, this left side is enabled, portion enabled, that this become the disabled. If this is enabled, this become disabled. At a time, we can do loading and unloading robotic problem. Suppose we have robot and we want to load some kind of thing, and we want to unload it. That we can do here simultaneously. Although a lot of properties are available, behavior properties we can analyze, structure property, behavior only based on the behavior, how the states are changes after other, and structure means it is based on the structure of the pertinent. What kind of structure, graphical or topology is there? We can have 2 kinds of property analyze here. So based on the behavior property, basically, I'm here with this one shape pattern K bounded. Basically, K bounded means whenever I am restricting the number of tokens, or in real life situation, if I wanted to show that when a system is stopped or absence or overflow, if I have such kind of situation, or I want to do model, right? So in that case, boundedness situation is play very important role. For example, this is the pertinent. I call it 3 bounded. Why it is 3 bounded? I'm not allowing more than 3 tokens at all. Whenever I fire all the transition, you can see here that is a reachability tree of this pertinent. If I construct the reachability tree here, so you can see no token, no place receive more than 3 tokens. So that means this place is bounded, 3 bounded, this 3 bounded, and this is true for all places. No place has more than 3 tokens. Hence, this pertinence is 3 bounded. That means we are restricting the information or flow of information up to the 3. We can also fix some other number, maybe the K bounded. It can be so. And very beautiful, very important property is that if I restrict the K equal to 1, the 1 bounded means we are allowing only maybe the 0 token or 1 token here. 1 means save. So now we are with the binary sequences here. I will for this binary sequences, I develop the entire theory on in the collaboration of our lab mates or students. We have proposed the theory based on the Boolean pertinent, where we study some kind of binary sequences. It is well proposed theory already available in the literature. If anyone interested, they can use that theory. The theory can be used in to study the lattice kind of a complex kind of structure, and to generate the n-dimensional binary Boolean lattice cube. It can be used, or we can also develop our own software, indigenous softwares. And this is one example. For example, we have one or single traffic light, or we want to model such kind of, that is beginner. I have put it here, very simplest example for the beginners. Suppose we want to model the lights, traffic lights. Traffic light means we have three kinds of colors: red, green, and yellow. And start of green, these can be taken as the axons. These are the transitions basically. And red, green, and yellow. And red means token in red means the red light is going on. Right? Whenever counter, we set the counter or we set the firing of the transition, because there is a concept in the transition in this pettinate that another class of the pettinate. This pettinate class is called timed pettinate. Timed pettinate is called the timed pettinate, also available. Fine. If we assign the timer here after 30 seconds, 40 seconds, we can assign. Then this red light token is shifted to the green line. That means green light is going on. So in this way, we can model and green to yellow the traffic light. That is an instance for the single traffic light. Okay. So whenever we have in metropolitan city some traffic problem, we can model the multiple lights, traffic light. We can be model. It is possible as per our requirement. Multi light traffic lights. Right. So that is the example. Liveness also other example, that is live means the system never end. For example, if you model our seasons, spring, summer, autumn, and winters, and start of summers are the transitions. And okay, then this token will move from here, then to autumn to winter, like this. It can be model, and we can visualize the changes. Okay, and we can also use the intermediate weather in between the spring and summer. That also it can also be modeled with the help of pettinate. Fine. Conservatism, I'm leaving that property that whenever token sun is less is same or not. And one more property, I just wanted to hear how we can use, or what is the use applicability of the place invariant. Okay, no, I'm not considering any example. Suppose you are using the place invariant property, means set of places in which the total amount of token is constant, suppose. Fine. So in that case, what do you mean by this? We large number of reactions that occurs in the organism, means identification of place invariant means identify reactions that constitute a pathway. That means we can identify the pathways, okay, with the help of the place invariant property. Similarly, we can use the transition invariant property. We can check the such kind of state continuous operation. We can use state whenever the system is continuous or not. If we use such kind of transition invariant property, it is given in the literature. Well-defined literature is given. Circuit we can also use to analyze the in metabolic pathways. Also I have used in our research papers. Okay, quickly, just another example. Beautiful, very simplest example is this. We can also use this pettinate in modeling of the chemical systems. Suppose we have three system of equations. Maybe this is the carbon. Whenever carbon molecule atom combine with the oxygen molecule, it releases carbon dioxide. Here equation can be modeled as a transition. One equation, this is second equation, this is third equation. Fine. And the atoms or the molecule can be taken as the places. Okay. And the amount means I'm not considering actual amount. I'm using the simple pettinate here. Okay, but this actual amount can be considered in another kind of pettinate is the continuous pettinate. Okay, so here dot means or token means the carbon atom is present, oxygen is also present. I'm not saying the how much quantity, how much amount of carbon or oxygen are present here. I'm not saying like this. Okay, so here whenever transition enabled means whenever the reaction reaches to the some kind of reactive condition or some temperature or something, if it condition is met, okay, the reaction will start and the change of start happening in the reaction. Basically, this is nothing. This is the one kind of synchronization. If you see this, fine. That means this number of token that will consume from the input place, that will deposit here in the next step. You can see here. Okay. Similarly, whenever release of carbon dioxide, whenever carbon dioxide react with NaOH sodium bicarbonate, that will release the NaOH CO3 here. Fine. And NaOH CO3 HCl that will combine, that will give you release the H2O, water molecules, carbon dioxide, H2O, and the token move from here, that you can see here like this. So in this way, we can use whenever we have, it is simplest, maybe it is very simple by looking here, but whenever we have set of n number of set of equation, so it is very difficult to model or understand such kind of complex set of equation. So in that case, if we use this, so we will get a very good visualization, also the intermediate state, if the construct is reaching tree. So it is very, very useful techniques, right? Same thing we can also use in some kind of other research area. Basically, we can also use the pattern modeling biodiversity. If we want to check the biodiversity system is balanced or not, we can use, for example, I have designed this example. Suppose these are some reasons, okay, and these are the causes basically, okay, and maybe the plant one, lake, animals. Similarly, we have R and M plants we have, and lakes and R animals we have. Okay, whenever cause one is there and the condition met, the token movement will start. Our concern is that whether we are able to achieve the balance biodiversity or not. Means whenever we are able to transfer all the tokens from here to here, or we can say if all places has a token here, that means oxygen is available, food is available, medicine is available, water is available, enjoyment is available, clothing and several things are available. Fine. So in this case, we can say that this state can be achieved. Okay. If we have large number of factors or many factors, so in that case, we can analyze this kind of systems or use in modeling. Okay. And computer is possible, it is there. Okay. So here I can show you the last slides here. So I will be able to find here all the places nodes has a token. That means it shows that the presence of something. If even a single token is not available, that means absence is there. The biodiversity system for the humanity is not balanced, because we cannot live without water. We cannot live without medicine if token is not there. We cannot live without the oxygen if token is not there. Right? We can check the several properties, behavior properties. Okay, and we can also have some other question. Is it possible to reduce the size of such kind of network? Yeah, it is possible, but we need to. It can vary problem to problem. How we can optimize the size or number of places or number of transition of firing sequences. That is possible, but it always vary with problem to problem. Right? Let us suppose a very beautiful example. We have heard of how to model the logical puzzles. Basically, puzzle is there. I just wanted to put here how we can convert the puzzles in terms of the problem form. Right? We have this puzzle. Everyone knows about this puzzle. Wolf, goat, and cabbage is there. The four come to the river that they must cross. There is a boat available crossing the river, but it can carry only one and at most one of the object. Okay, the wolf may eat the goat whenever man is not around. Similarly, goat may eat the cabbage not unattended. The question is, can the man bring everyone across the river without endangering the goat and cabbage? If so, fine. So how we can convert in terms of the problem? I will leave it some intermediate state, but how to convert? Just okay. Left side rivers, all fours are available. River is there. We need to check that whether all four can reach right side or not. That means whether this state is reachable from this state or not. That is the problem basically. Is it possible or not? Now I can assume objects. I can assume man, wolf, gate, goat, cabbage, boat. And actions are whenever crossing the river, wolf, eat goat. These are the actions basically, or activity. State means the presence of the object, that is the of any wolf, man, that is the token or the marking. Fine. So now the problem is that it's scientific, it's well defined. Problem is that how we can write it? Can the man bring everyone close the river? That means is the state. State means marking. Marking means man at the right side, wolf at the right side, goat at the right side, and cabbage at the right side. Reachable from the state, man is the left side, wolf at the left side, goat at the left side. L stands for left side, without endangering the goat or the cabbage. This is the problem. Is this state reachable or not? Similar way, we can convert our hypothesis, our problems in this way, and we can do the analysis with the help of PetNet. Fine. So these are things I just model here. Okay. For example, the time is less because I will not explain all. Let us suppose. Okay. So in this case, the token from here input place will consume, and the token will deposit via this here and in this place. You can see here. Okay. So now man, the pen and wolf and cabbage can live together, can stay together in the left side, because wolf cannot eat, never eat the cabbage. Okay. So that is why man at the first step, man and goat will go together in the right side, and right side these are there, and the man will leave the goat right side as it is and come back again like this. And at the end, I can show here, at the end, the all places will receive the tokens here like this. Okay. So that means this is possible. This state is possible. That means this problem is solvable. We can also say. Okay. This is in this way we have such kind of presence of in the right side, man is available, wolf is available, goat is available. This problem is solvable. If anything is not available, that maybe we are not able to solve, or we are not able to shift, to transfer, or to cross the some left to right position. Not solution, not complete possible. Complete solution not possible like this. Okay. We can also use in computer step, for example, if we consider this expression here, left side, okay, we can use addition can be taken, any kind of operation can be taken as transition. We can use it and we can solve, we can find such kind of solution like this. Okay, this is possible. Okay, in the same pattern, we can write our own code, okay, and we can train the machine. For machine learning, we can one kind. We can introduce, we can create, and we can find a solution very less as compared to available whatever time is given for the compile time. We can get the alternate solution or minimum time or less time we will get. Okay, like this. And I just wanted to show here one more important things here, that another class defined by us, Boolean PetNet. That means we are restricting the number of tokens in our this is research topic, hot research topic right now. Okay, the only 0 or 1, or that means one safe PetNet. Safe means we are allowing only 1 or 0 tokens. Fine. So here we define this kind of PetNet, and we have seen that it contains all the binary and sequences in its reachable tree. Okay, so that kind of PetNet is called Boolean PetNet. Fine. So now there are two classes of the PetNet. One is the Boolean, one is the crisp Boolean. This is the crisp Boolean. Crisp Boolean means in this one we have all the binary and sequences. That means 2 raised power 3 sequences, because we have 3 places are there. Repetition is also there. Repetition is also available. But in the second one, that is called the crisp Boolean, means crisp Boolean, repetition not there. All marking vector appears exactly once. There is no repetition. Okay, if there is no repetition and all binary and vectors are available, that is vectors are available. Okay, possible repetition, that is the Boolean PetNet. Two classes are we define 2 classes. Theorems we have proved, and important thing is that even if I remove the center transition from here, I'm with the n component of this one component and one component like this. So similarly, I can have this component, n component. You can see here. Okay. So here, if I fire all the strategically fire. Okay, not the normal firing. Strategic fire means we are firing the transition in orthogonal direction. Orthogonal means, it doesn't mean the transition fire at a 90 degree. It doesn't mean that, because we have n number of transition, every transition fire at the different direction that I'm assuming it is as a orthogonal direction. Okay, so whenever I fire on the transition, so now you can see that is nothing, it is a homomorphic image of the complete Boolean lattice of the reachability tree of this. Okay, once again I'm stating here, if I construct the reachability of this kind of patinate, okay, and this, the reachability whatever I have here, like this, the patinate reachability I have here, okay, and if I use some kind of homomorphism in this reachability tree, then what I will get here, it is a complete Boolean lattice, cube lattice here. So similarly, if I have n number of places, or like this, these components, I will be able to generate n dimensional Boolean lattice. It is already published result in the literature. Okay, so in that case, we can use assign. We can use 0, 1 bit as some kind of information. Okay, maybe some kind of data, and that is very useful to reduce the dimension of the cube or increase the dimension, because we know the property of the cube, it can be obtained recursively, higher to lower, lower to higher dimension. Both way it is possible. If we are reducing higher dimension, we are increasing the firing steps, and we are number of transition we are increasing. If we are reducing means higher to lower, that means we are reducing the number of transition, and just automatic firing or just triggering the transitions, we will have all the states exactly one, as we can see at the corner or vertices of the n dimensional cube. It is very, very important result we found in our research last 10 years. Other applications also we use, we have done the CRB funded project. Okay, we have find some kind of diagnosis in tuberculosis pathways. We have find the result is already published, and we have find longest diameter, and such kind of description we have taken, the places and transition you can see here, and such kind of property we have analysis, net density, average number of these are the properties of the patinate. I'm not sharing here, but it is available. We have discussed based on these ratio metrics of the parameters, we conclude some kind of early stage treatment, early stage detections. Okay, in this way we have used. Also, we also use this kind of work in some kind of plant biology or plant science. Okay, in to modeling the C3 and C4 cycle. Okay, although papers is not complete article, but it is available on some kind of online repository that was not completed, but it was there. We model that. Also, we try to use in finance. Okay, now you can see whenever we have 6 places here. So in this case, it is very, very difficult. Such kind of complex structure we have. All possible number of states are available. We can easily generate. Okay, for this we have some kind of software. I can show you. Then I will stop here. We can I can allow have interactions. We can have some questions. Okay, some work is available, and some laboratory work done. Several students, 4 or 5 students, they got the PhD recent to 4, 5, 6 years in our lab. Okay, so now I just wanted to show here some kind of software demonstration here. Let us suppose I'm sharing the screen of this. Okay, that is a software I'm using here, pipe. Let us suppose if I construct, I just can show you very live demonstration here. Okay, so here let us suppose I have 3 places. Arcs I'm using here. Okay, this is for the whoever interested in practical or applicable work, not the theoretical, they can use it. And let me add some kind of tokens here by using this. If I add the token, and if I run, there is an icon in green one. If I run this, so they are in the left side some kind of property analysis they can see directly. So here, if I run this program, and you will see some kind of cubic like this. Okay, so here where the problem arises, it is easy, only 3 places. Now you can see here, if I change only one token, if I add the one token here, one token, let us suppose, in every places, if I add. Now you can see what kind of exponential growth will be there, will be arise in the network. Okay, now it is you can see here, right? Again, let me change the number of token or increase the number of token. So maybe there is a possibility my machine not allowing or not having the configuration due to the computation step. It may not be run. Let me check it is whether it is done or not. You will see here. So what is showing here? Yeah, now you can see the size of the network. It is increasing exponentially. Just changing the one token in each and every places. Okay, so in that case, whenever you want to study the crystal time structure, lattice time structure, okay, you can use several properties of the pettinet simulation. Also, modeling you can use here such kind of results. Okay, these for this we have some kind of literature available. What is the meaning of average number of token or 95? How much confidence you have with your results? Simulate, basically you can simulate the results. Okay, several analysis can be done in the left side. A theoretical way it is also available, because I already told you in the beginning, it can be used in several areas. Okay, and I'm not able to find even a single area where the pettinet concept is not applicable in real life situation. I'm not able to find. If anyone has such kind of, then we can have discussion. We can explore our area. So, at last, it is very useful theory as well tool as well as applicable mathematics or techniques. Also, we can say it can be used multiple areas due to the variations of the pettinet by his nature. Again, I'm telling you here, it can be simple kind of pettinet. It can be hybrid pettinet. It can be stochastic pettinet. It can be continuous. Can be fuzzy. Okay, I think more than 20 kinds of varieties are available in literature. Okay, and right now it's very growing area. And yes, can be applicable in cancer, because you can see the exponential growth of the tokens, exponential, because cells are increasing exponential. Okay, you can suppose you want to use the all kind of states are available. Okay, so for this we have theory. I can give you the idea. We have proposed the theory, the binary pettinet. Okay, we propose the theory. Binary means we characterize the trees where the trees are perfect binary and complete binary, or we define such kind of things. It can be used. It is already there. Even I can, if you type on the Google, you will see several things, the practical applicability in the Alzheimer also. Okay, heart, cancer. Let me show you my live here. Let me put here pettinets in cancer. Okay, modeling. You will see several articles. You can see in the lively. Okay, I can show you here. Okay, now you can see modeling analysis. Okay, breast tumor. They have used the colored pettinet. CPN means colored pettinet they have used. Okay, so lot of areas you can use. Okay, you can see if you put it there, you will get lot of things you will get. Okay, it can be seen as just like a topology, pure mathematics, and it can also be seen just like a applied mathematics. In both ways, we have theory and application in different areas, and the researchers published their article very high impact factor journal. Okay, more than 20. Even Nature, you will see several articles by written by using things. You can see one article here. BMC, it's very good journal. Okay, and also National Center for the biotechnology information, they have modeled some kind of things. So lot of literature available. Okay, but thing is that you must understand the concept. Okay, it is basic as well difficult. Both kind of way it can be seen, and how to use. What is the fundamental thing? What is the fundamental things are required to model the pettinet? Because in pettinet we have firing flexibility, because transition is ready, actions are ready. Up to you whenever you fire or not. Okay, for example, you have disease. Okay, and you want to take the treatment the disease. or diagnosis you want to do. Okay, you want to take the diagnosis or not, up to you. Okay, so that is why it is very, very important. Okay, if any question, any doubt, I'm happy to discuss with you. And fundamental books are, because one book is this is the JL petition, the first book of the patinate. It can be found, it is online available. JL Peterson in 1981 it was written. Okay, and pure mathematical point of view, there is a Rizig book is there. Rizig book, Springer, there is a monograph is there. Rizig, okay, book is available. One is the JL Peterson. Okay, Peterson. This is the application point of view. This is the pure point of view. First one. Okay, one is 1981, second is 1982. And the cancer biology, I think in the last year, I have more than 250 books are available. I have checked at time. Okay, after that, I think several update every day we will have. Okay, it is available. If you, even several books are online available, right? And computational biology, even if you check some keyword, if you write computational biology, within that chapter you will see some kind of patinate. Okay, and last time I have also published one chapter in health related book. It is published by Springer book. It is there in my Google page, you can see. Okay, and although my pages are not updated, I didn't get the time to update, but it is available. Okay, yeah, any software it is there. For example, Pipe, Moped, and so I will suggest you use your own programming skills, Python or some other skills, or any C. C is also physical, because you can use your own logic, and the logic is theory also given. But also there, Charlie is there, Pipe, Moped, Charlie, several software, and if you are using the MATLAB, there is a patinate tool, simulator tool is also available in MATLAB. Yes, any other questions you can ask? Good, it is very difficult to say good. It is your, as per your requirement. You can use your maybe the some property are available in some tool, or maybe some other available in other tool, because the tools generally works on some particular theory. Okay, if they have add-on package, it will be there. Otherwise, you may your program. Okay, you need to find some other way. So that is why I'm telling you, you can write your own code in Python language. It is online, freely available. Our students are doing the same thing, and one software we are trying to develop in next 4 to 5 months. We have developed done around 70% work on this Boolean simulator tool in our lab. Any other question? Now I'm stop. Can I stop now?
Any question, please?
Yeah. Because this is the area is very interesting area of the research. Yeah, references you can see actually. If you our references you can also see. Even you just type on the Google, and books means I'll suggest you Rizig book and JL Peterson. These are the fundamental. I'm suggesting reason is that because these are first fundamental books written. Okay, after that variation you will see found several variations. Fundamental books are only these two books I found on the literature.
Okay. Any question more? I think there is no question.
Okay.
Thank you, sir, for your valuable lecture and spend time with us.
My pleasure, sir. Because you have conducted very good events, actually.
Thank you, sir. Thank you.
Thank you so much, sir. Thank you very much.
Okay, sir.
Can I stop now, sir?
Yes, sir.
Yeah. Thank you very much for giving the opportunity, and thank you, sir, Pradeep, sir, and Dr. Apana. Thank you very much, and our colleagues and audience for listening patiently last half an hour. I'm very happy here to be the part of it. Thank you very much, sir. My email ID kajendra@mail.jnu.ac. I'm writing here. Yeah, I've written my email ID. You can check it. Right, current updated. And if anyone, if you have any student they want to training, they can visit our laboratory. We are allowing and currently 4 or 5 students outside our JNU. They are coming. They are doing their dissertation, and we will be very happy to felicitate because we want to explore such kind of things in other areas as well, because we have something in our hand, our indigenous theory. Then it can be, it should be used, applicable in other areas as well. Theory we have, implementation we are looking still.
Okay, thank you, sir.
Thank you, Ji.
Okay, now our next lecturer is Dr. Sunil Kumar. Dr. Kumar, I think you with us, sir.
Yes, sir.
Okay, sir.
Yeah, thank you so
Dr.
much.
Kumar is an associate professor in NIT Jamshedpur, and sir will deliver his lecture on basic information on mathematical and empirical modeling. I request, sir, you start your lecture.
Hello.
Yes, sir, you are audible.
Yeah, thank you so much, sir.
Yes,
good
sir.
afternoon, everyone, and welcome to my talk. Thank you so much to Dr. Krishna Pada Das and Pradeep Rao, sir. First, I would like to express my sincere thanks to the Department of Mathematics, Mahadevananda Mahavidyalaya, Kolkata, and further extended my sincere thanks to Dr. Krishna Pada Das and Dr. Pradeep Rai for inviting me for this talk. Further, my sincere thanks to all members of organizing committee for organizing such wonderful faculty development program on recent trend in biomathematics and dynamical system, bifurcations, chaos, and numerical methods. In my view, this faculty development program is very beneficial to the especially young researchers and scientists, those are working in the field of applied mathematics. I hope this faculty development program is very fruitful and amazing to the all respected audience. Once again, thank you so much to Dr. Krishna Pada Das, sir, and his entire team for giving me such opportunity between many experienced, respected audience. I wanted to thank you very much for your excellent management who are directly and indirectly involved in this nice faculty development program. Thank you so much. Sir, I am sharing my PPT.
Okay, sir. It is visible, sir.
Yeah, thank you so much, sir.
Yes.
Yes, sir, my PPT is visible.
Yes, sir.
Yeah,
yes.
Thank you so much, sir.
Yes.
Title of my talk is Basic Informations on Mathematical Modeling and Epidemiological Modeling. Basically, I have a research involvement in different research areas such as fractional calculus and its applications, mathematical modeling, epidemiological modeling, mathematical physics, numerical analysis, Veblet method for fractional differential equations, non-linear dynamic and chaos modeling, and last one is chaos and synchronizations. And this talk is subdivided into few number of sections. First one is basic idea of mathematical modeling. In this section, I have given some basic definitions and basic informations related to the mathematical modeling. And next one is the basic idea of epidemiology. In this section, I have given a brief introductions about epidemiology. And next one is basic idea of fractional calculus. And next is Hermite-Veblet method. Next is fractional Kensel dynamical model. And we have find some numerical result and discussions. And last one is conclusions of this work. So first is basic idea of mathematical modeling. Actually, this part is very interesting part, because if we are working in the field of applied mathematics, then almost researchers are using mathematical modeling. So this is very interesting topics of applied mathematics, that what is mathematical model and what is mathematical modeling. So this is very interesting topics. So first one is this is very interesting question, that what is mathematical models? A mathematical models is a representations of the behavior of real objects and phenomena in mathematical concept and language. Mathematical model can take many forms, including dynamical systems, statistical models, differential equations, or game theoretic models. So this is the basic definitions of the mathematical model. And next one is the application of mathematical models. Mathematical models and modeling has wide applications in many research areas. So mathematical models are used in first one is natural science, such as physics, biology, earth science, chemistry. And next one is engineering disciplines, such as computer science, electrical engineering. And last one is non-physical system, such as economics, sociology, and political science. So mathematical models has a wide applications in many more areas in mathematics, physical science. Next is mathematical modeling. Actually, mathematical modeling is the process of developing a mathematical model. This is very interesting definitions of mathematical modeling. That in the other way, we can say that mathematical modeling is the process of expressing a real world problem in mathematical terms, usually in the form of equations, in the form of OD, in the form of PD. We can represent any mathematical models. And categories of mathematical modeling. Basically, there are two categories, main categories of mathematical modeling. First one is theoretical modeling, and next one is experimental modeling. So this is the basically two main category of the mathematical modeling. Theoretical modeling. In theoretical modeling, the system is described using equations derived from physics. For example, mechanical system, such as Newton's and Hooke law. And next one is electrical system, such as Ohm's and Kirchhoff law. Hydrodynamic systems, such as Bernoulli and conservation of mass law. And last one is thermodynamic system, such as ideal gas law and entropy. Systems which are modeled entirely based on physical principle are called white box models. So this is the basic idea of theoretical modeling. And next one is experimental modeling. Basically, experimental modeling is totally based on the measurements. The mathematical models of the system is derived from several set of measurements, each recording the system output for different inputs. Systems which are modeled entirely based on experimental data are called black box models. So this is the basic information regarding the experimental modeling. And next one is the next part is very interesting part, that classifications of the mathematical modeling. There are different type of mathematical model available. Some of them are listed below. First one is static versus dynamic. And next one is linear versus non-linear. And next one is explicit versus implicit. Next one is deterministic versus probabilistic. And next one is discrete versus continuous. And last one is floating, inductive, or deductive. So this is the main classifications of the mathematical modeling. And next part is what are objective and advantage of mathematical modeling. This is very interesting questions, that what are objective and what are advantage of the mathematical modeling. So objective of the mathematical modeling, basically mathematical modeling is a process that uses the language of mathematics to analyze any mathematical model and make predictions for models, provide insight of the real world problems, and find optimal solutions of the real world challenges. So this is the main objective of mathematical modeling. So we can find these points about any mathematical models. And next one is the advantage of mathematical modeling. This is very interesting part, that what are the advantages of mathematical modeling, why we are doing mathematical modeling in each field. So mathematical modeling and models can represent the reality quick and accurately. This is a advantage of a mathematical modeling and models. Model can help a decision maker formulate problems. Modeling and models can give us insight, informations, and improve our understanding of the real world problems. And modeling and models can save time and money in decision making and problem solving. A model may be the only way to solve some large or complex problem in a timely fashion. Modeling and models can be used to communicate problem and solutions to others. Modeling and model can help to provide predictions and control. So this is the advantage of the mathematical modelings. Next part is what should characteristic of mathematical model. Characteristic of mathematical models: the model should be as simple and understandable as possible. The model should be reasonable. The model should be easy to maintain and control. And next one is the model should be adaptive. The parameter and structure of the model should be easy to change as new insights and information involved. The model should be complete on important issues, that is, all important variables and factors should have been taken into considerations. So this is the main characteristic of the any mathematical models. And here I have presented a graphical representations of the mathematical modeling process. I have presented a mathematical process through this graphical representation, that first we have considered a real world problems, and again we simplified this real world problem into a simplified models. Again we converted this simplified model into a mathematical model. Again we converted this mathematical models in computational model, and we have find some results regarding this model, and we interpreted the real world problem through these results. So this is the mathematical modeling process. Real life example of mathematical modeling. Actually, we have presented 3 examples of the real world problems of mathematical model. First example is launching a satellite. We are using mathematical modeling behind the launching of a satellite. This is the very interesting examples of the mathematical modeling. And second example is predicting the arrival of the monsoon. Behind this, we are using mathematical modeling. And last example is reducing traffic jam in a big cities. We are using mathematical modeling in this reducing the traffic jam in big cities. These are the very interesting examples of the mathematical modeling. And next part is basic idea of epidemiology. What is epidemiology? Actually, origin of epidemiology is derived from Greek word epidemic, epi, which means on or upon, among, demos, which means the common people, logy, which means study. So here I have presented some historical evolutions of epidemiology. And the first Hippocrates, the first epidemiologist, Hippocrates, has presented some good research in this field. Hippocrates was a physician who became known as the father of medicines and the first epidemiologist. He has published some interesting books on related to epidemic. First is entitled Epidemic 1, Epidemic 3, Epidemic 1, Epidemic 2, and Epidemic 3. He observed that different diseases occurred in different locations. Hippocrates identified hot and cold disease, consequently hot and cold treatments. And next one is Thomas Sydenham. Thomas Sydenham was successful petitioner and witnessed more than one new editions of his various theses called for in his lifetime as the father of English medicine. He has published some books related to medicals. He treated smallpox with bed rest and normal bed covers. And next is James observed he has published some interesting research papers, and he has published some books entitled A Thesis on Scurvy in 1754. And next one is Professor Jenner. He has worked in this field, and some more researcher has pay attention in this field. And next one is, what is epidemiology? Actually, many scientists has given different definitions of epidemiology in own style. Researcher Parkin in 1873 has given a definitions of epidemiology that the branch of medical science which treats epidemics. In 1927, Frost has given another definitions of epidemiology that the science of the mass phenomena of infectious diseases. In 1934, Greenwood has given the definitions of epidemiology that the study of disease, any disease as a mass of phenomena. And McMahon in 1960 has given another definitions, the study of distributions and determinant of disease frequency in man is known as epidemiology. In 1988, the John M. Last has given another definitions that the study of the distributions and determinations of health-related states or events in specified populations and applications of this study to control of health problems. So many scientists have given definitions, different definitions. Component of epidemiology. There are 6 components of epidemiology which has presented in this graph. And component of study, frequency, distributions, determinants, disease and other health related events, human populations. And objective of epidemiology: to identify etiology or cause of a disease and the relevant risk factor, to determine the extent of disease found in the community, to study the natural history and prognosis of disease, to evaluate preventive and therapeutic measures and modes of health and healthcare delivery. And last one is to provide the foundations for developing public health policies. Next is branches of epidemiology. There are 8 branches of epidemiology which have presented in this graph. And next one is few example of epidemiology. There are so many examples of the epidemiology, but I have presented some examples of epidemiology, that blood pressure, anxiety, depression, dengue, malaria, COVID-19, HIV, AIDS, cancer. There are so many examples of the epidemiology. Epidemiological modeling. Epidemiological modeling can be a useful tool for disease prevention and control, as well as creation of animal health policies. And epidemiological modeling is a simplified means of describing the transmission of communicable disease through individuals. These simplest models are formulated as a initial value problems for system of order differential equations. Epidemiological models should not be viewed in isolations from data from laboratory and field research, because they are only one instrument for giving technical guidance. And next part is, why do we need epidemiological modeling? Even the vaccine are available for many infectious diseases. These disease cause suffering and mortality in the world. In developed countries, chronic disease for death such as cancer and heart disease receive more attention than infectious disease. Recently, some infectious disease like HIV/AIDS, which can lead to AIDS, has become an important infectious disease for both developing and developed countries. And epidemiological models use a microscopic descriptions. Epidemiological modeling can use to compare different disease in the same populations. And next one is, epidemiological models are used in comparing the effect of prevention or control processes. And type of epidemic models, I have presented a type of epidemic model through these graphs. And next is, what is the benefit of epidemiological study for biologists? This is very interesting part. That benefit of epidemiological study for biologists: acquiring detailed knowledge of the mechanism behind disease. Example, risk factor, specific pathogens for infectious disease, treatment with antibiotic during the investigation period, informations on symptoms of illness. There are so many benefits of the epidemiological modelings. In the basic model, I have presented some basic models like SIS models. If the recovery does not give immunity, then the model is called an SIS model. It is appropriate for some bacterial agent disease such as agent disease. Next one is SIR model. If the individuals recurs with permanent immunity, then the model is called the SIR model. It is an appropriate for viral agents such as measles, smallpox, mumps. And next one is SIRS models. If individuals recurs with temporary immunity so that they become susceptible again, then it is appropriate for SIRS model. Some others models with more compartment like SEIS, SEIR, MSIR, MSEIR, and MSEIRS models. Advantage of epidemiological modeling: inexpensive and not time consuming, suitable for rare diseases. Next one is suitable for disease with long latent periods. Next is no drop out problem, preventions and control of disease. Next one is identifications of clinical syndromes. And there are so many advantages of the epidemiological modeling. Here I am going to give some brief introductions about the fractional calculus. So fractional calculus has two directions. First one is classical calculus, and next one is the fractional calculus. So this is interesting question, that what is fractional calculus? What is classical calculus? Classical calculus, the meaning of the classical calculus is the study of continuous change of functions. Most of these quantities are the functions of time, such as velocity is equal to change in distance with respect to time. The two major concepts of calculus are derivatives and integrals. This is the main part of the calculus. So the classical calculus deals with a positive integer order derivative. Actually, we are familiar with the normal derivative, first order derivative, second order derivative, third order derivative, and nth order derivative, where n is a positive integer. In the similar manner, we are familiar with the first integral, double integral, triple integral of a functions. And this is the part of classical calculus, but again we are going to learn about fractional calculus. So what is the fractional calculus and its initial birth? The birth of fractional calculus was the end of 7th century to a statement made by French mathematician L. Hospital to German mathematician Leibniz, that in a letter of L. Hospital in 1695, Leibniz raised the following questions: that can the meaning of derivative with integer order be generalized to derivative with non-integer orders? Then L. Hospital replied by another questions. The story goes that L. Hospital was somewhat curious about that question and replied by another question to Leibniz, that what if the order will be 1 by 2? Leibniz, in a letter dated September 30, 1695, replied, it will lead a paradox from which one day useful consequence will be drawn. These extraordinary questions of L. Hospital laid the base of fractional calculus. The question raised by Leibniz for fractional derivative was an ongoing topic in the last 300 years. So fractional calculus is the study of non-integer order and integral of real complex order. For example, nth order derivative of y is equal to dy by dx if n is equal to 1. If n is equal to 1 by 2, then we are getting half order derivative. This is fractional differentiation when n is a non-integer. The fractional calculus is an interesting and novel topic of the research area of applied mathematics. Fractional calculus, in a different way, we can say that fractional calculus is the extension of ordinary differentiation. And fractional calculus provide a good tool for describing many physical phenomena. And in 1819, F.S. Lacrosse became the first mathematicians to publish a paper that mentioned the fractional derivative and offered the correct answer to the problem posted by Leibniz and L. Hospital. Lacrosse developed the formula for nth derivative for y is equal to t to power k. He has developed a formula of y is equal to t to power k, that nth derivative of y means t to power k is equal to factorial n divided by factorial k minus n into t to power k minus 1 n, where k is greater than or equal to n. Lacrosse derived the formula for the fractional derivative by replacing the factorial in the gamma functions. Actually, factorial and gamma has a relation, then factorial k is equal to gamma k plus 1. So we have replaced this result. Then we are getting alpha order derivative of t to power k is equal to summation k plus 1 divided by gamma k plus 1 divided by gamma k minus alpha plus 1 into t to power k minus alpha, where k is greater than 0. For a particular value of k is equal to 1 and alpha is equal to 1 by 2, we are getting this result. So this is the result for a special value of k is equal to 1 and alpha is equal to 1 by 2. And next one is the fractional integration of order alpha is defined by this formula. Here the suffix alpha represent the fractional derivative of integration and I represent the integration sign with respect to t of functions t to power k is equal to gamma k plus 1 divided by gamma k plus alpha plus 1 into t to power k plus alpha. Again, applications of fractional calculus. Actually, fractional calculus has the wide applications in many research areas such as physical science, biological science, and there are so many fields in this. It has wide applications in many more research areas such as physical science. There are several physical problems are considered and formulated by many researchers with the help of fractional tools such as heat equations, wave equations, telegraph equations, gas dynamic equations, Navier-Stokes equations, and many more physical equations. And my team has published some good research publications in related to these problems. First one is new analytical method for gas dynamic equations arising in shock fronts. We have published this paper in Computer Physics Communications. This is SCI journal. And another paper we have published in Applied Mathematical Modeling, a new analytical modeling for fractional telegraph equations via Laplace transform. Another we have published paper in nonlinear dynamics, which is SCI journal. And we have published another paper in mathematical method in applied science, which is based on new operator Yang Abdel Katani fractional operator on physical problem heat equations. So this is another. So we have published some good papers. Next is biological science. Epidemic model. Nowadays, research on epidemic model are very famous research area by adopting numerical methods. And my team has published some good papers on some biological epidemic model like HIV/AIDS model, COVID-19 models, Ebola virus model, cancer model, tumor model, dengue model, and many more epidemic models. And my team has published some some research papers related to these epidemic models, like a study of behavior of immune and tumor cells in tumor model with non-singular fractional derivative in Cass-Salter fractal journal. This is SCI Q1 journal. And next one is a wavelet-based numerical scheme for fractional order SEIR epidemic of measures by using Ganachie polynomial, which is published in Numerical Methods for Partial Differential Equation. This is another paper, a robust study on COVID-19 outbreak through non-singular derivative. This is published in European Physical Journal Plus. And next one is eco-epidemic model, and research on eco-epidemic model are also an interesting research area, and many researchers has paid attention on it. First one is pre-predator models, host parasite models, plant disease models, Lotka-Boltra models, potato leaf roll virus models, and there are so many eco-epidemic models. And my team has published some research paper on these eco-epidemic models. First one is chaotic behavior of fractional predator pre-dynamical system, which is published in Cass-Salton's Fractal Journal. And next one is a study of fractional Lotka-Boltra populations model using Haar wavelet and Adam Basco's motor method, which is published in Mathematical Method in the Applied Sciences, which is Q1 journal. And next one is a study on fractional host parasite population dynamical model to describe insect species, which is published in Numerical Method for Partial Differential Equations, which is Q1 journal. And fractional calculus has a wide applications in other many more areas such as chemical science, gas theory, financial mathematics. And during the 18th and 19th century, many great scientists contributed significantly to the development of fractional calculus. The name of few are given in this slide. And few interesting definitions of fractional derivative are given as Riemann-Leibniz fractional derivative, Kapto fractional derivative, Will fractional derivative, Rist fractional derivative, Hadamard fractional derivative, Chen fractional derivative, Jumaria fractional derivative, Yang fractional derivative, and last two definitions are the Kapto-Fabrizio fractional derivative and Etangana-Baleno fractional derivative. Here we can see that first two definitions are the singular definitions of the fractional derivatives, and last two definitions are the non-singular definitions of the fractional derivative. Here I have given some brief introductions about some great mathematicians like Riemann. He has published some papers on Riemann integral. and he has given both has given definitions of the fractional derivative. And then in next slide, I'm going to present some basic definitions of the singular and non-singular derivative. So first one is the Riemann-Leibniz fractional integral. The Riemann-Leibniz fractional integral is discovered by the Riemann and Leibniz in 1832. The Riemann-Leibniz fractional integration of order alpha is defined by this formula, and the suffix RL means Riemann-Leibniz, I means integration of function ut is equal to 1 by gamma alpha integral 0 to t ux upon 1 t minus x to power 1 minus alpha dx, where the value of alpha is greater than 0 and the value of t is greater than 0. The Laplace transform of this integral is represented by this formula, where the capital US is the Laplace transform of ut. And next definition is the Riemann-Leibniz fractional differentiation. The Riemann-Leibniz fractional derivative of order alpha is defined by this formula, and we can see that why we are saying that this fractional derivative is singular. Actually, this kernel has a singularity as t is equal to x. That's why this is known as singular definitions of the fractional derivative, and the Laplace transform of this fractional derivative is presented by this formula. And the capital fractional derivative, the capital fractional derivative is represented by this formula. This is another definitions of the fractional derivative, which is singular definitions of the fractional derivative, because it has a singularity as t is equal to x. That's why this is known as singular definitions of the fractional derivative. And next one is the Capito-Fabrizio derivative. This is the non-singular definitions of the Capito-Fabrizio derivative. That we can see that the Capito-Fabrizio derivative of function ut is equal to m alpha divided by 1 minus alpha integral 0 to t u dash tau e to power minus alpha 1 minus tau by 1 minus alpha d tau. We can see that this integral has no singularity. That's why this integral is known as non-singular derivative, where m alpha is normalization function such that m0 is equal to m1 is equal to 1. And the fractional integral associated with Capito-Fabrizio derivative is defined by this formula. And the next one is Etangana-Balanou fractional derivative. It is given by two mathematicians. First one is Professor Ebden Etangana, and next is Professor Dumitru Balanou. Actually, they have replaced this exponential functions in Methage-Leffer functions. Then this derivative is converted in the Etangana-Balanou fractional derivative. We can say that this derivative is more generalizations in compare of Capito-Fabrizio derivative. We can see in the definitions that in these definitions we are using exponential functions in Capito-Fabrizio, and in these definitions we are using Methage-Leffer functions. Actually, exponential function is the special case of Methage-Leffer functions. This is the basic definitions of the Etangana-Balanou fractional derivative. Here we are using e alpha minus alpha t minus j to power alpha by 1 minus alpha, where ab alpha is the normalization function and has property ab0 is equal to ab1 is equal to 1, and the e alpha is Methage-Leffer function. It is given by this formula, and the Laplace transform of Capito-Fabrizio derivative is given by this formula. We can generalize this result, then we are getting this result. Next one is the Laplace transform of fractional derivative is given by this formula. This is generalization of this result. And this is the Laplace transform of Etangana-Balanou fractional derivative by fractional order model. Actually, due to the complexity of most physical problems, the class of classical differential operator has failed to replicate the complexity of problem. Some problems have non-localities, including fading memory, long-range dependence, memory effects, power law process, fractal process, crossover behavior. So we are using basically fractional order models. And the next one is, this is a cancer model. We have converted of time fractional. We are using Kapto-Fabio derivative in the first term. Then this is the time fractional cancer model, and this is the initial conditions we are using in this. And these are the parameter which we have used in our model. UT represent the tumor model. First one, this UT. UT represent the tumor cells, and second VT. VT and WT are the immune effector. A represent the improvement rate of tumor cells. R1, R2 represent the reduction rate of tumor cells. D1, D2 represent natural decay rate of the effector cells. VT and WT. K1, K2 represent half saturations parameters. And in this models, we are using Hermite wavelength methods. We have formulated Hermite wavelength method, and we have find operational 6x6 operational matrix, and we are using this operational matrix for in the solving of our model. Then we have find this fractional order operational matrix for alpha is equal to 0.9. And again, we are using this method. We are getting some graphical representations related to this parameter which we have used in our model. This is the reference list. Thank you so much. Actually, time was less, though I have tried, I have explained in tried within 30 minutes. It is finished from my side. So there is any questions you can ask. Any questions, sir? Pradeep, sir. Hello. 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 Hello.
Sir, till then, I want to ask a question that
Yeah, please, please.
if you can tell me the current research topics in chaos regarding celestial mechanics and another topic regarding special functions collaboration. I mean, some special function in chaos theory.
Some special function in chaos theory.
Yeah, I mean,
actually, I'm not using special functions chaos theory, but we can say chaos theory.
Yeah, sir, I want to find some topic in the intersection of chaos theory and special functions.
You mean that you want to work in chaos theory with the help of special functions?
Yeah, that's exactly I want to.
Yeah, we can do. You can do.
Sir, how I can find those topics? Please tell me the process, sir.
Actually, sorry, I have no idea because I'm not using special functions for the chaos theory. Basically, I'm using chaos theory in the disease modeling. Okay, by using numerical methods. But we can, you can try it.
Yes, sir, but actually I am finding the topic. So if any help, any method by which I can easily find the topic.
It is better to work on disease modeling. Nowadays, disease modeling is a very interesting research area. Okay. Actually, spatial function is good topics, but this is totally applied mathematics. In my view, I am suggesting you that you can work in the field of disease modeling, epidemiological modeling related to numerical, I mean, using numerical methods. It is good nowadays. So you can work in this field.
Okay, sir.
Any question, please? Okay. Thank you, sir, Dr. Kumar,
Thank you
for
so
your
much, sir.
valuable
Thank you so much,
answer.
sir. Thank you so much, sir. Okay, sir. Can I leave, sir?
Yes, sir. Yes, sir. Okay.
Okay. Okay. Thank you so much, sir.
Now, please, all participants, please listen. There will be a break for 40 minutes. Okay. The next session will begin at 3 p.m. Okay. Our next session will be start from 3 p.m.
Okay, okay.
Okay.
Good afternoon. Good afternoon. Yes, I'm ready. Thank you, Dr. Krishna Das, for inviting me. So let me share the PPT, then we'll start. So now presentation is visible. Okay, thank you. So very good afternoon to all, and thank you very much to the organizer for inviting me to deliver a talk in faculty development program on recent trends in biomathematics and dynamical system. So today I will talk about some application of the fluid dynamics in biological transport phenomena, which is the theme of this faculty development program, that is biomathematics. So the application of mathematics in the biological transport phenomena will discuss by using the concept of yes, it is possible. It is possible. Now it is fine. Moving. Okay. So this model will be the application of mathematics in biological transport phenomena, and we'll talk about the concept of fluid properties and the fluid dynamics, how we can use the principle of the fluid dynamics in the biological transport phenomena. So that is the objective of this model. And the title of this talk is Analysis of Rheological Behavior in the Membrane-Based Pumping Flow Model. And application will discuss in the biological flow, because membrane is one of the natural muscles in the body, and that will work in the form of some propagation, or which create the pressure, and due to that pressure there is a movement inside the body for the biological fluids. So that will work as a pumping mechanism, and that is very important. So with the help of that concept, we have developed some models, and then we have seen that what type of effects of the rheological property of the fluid will be there, and how we can recommend such parametric analysis for the biological transport phenomena. So this is the main objective. As we know that fluid is having the various type of or fluid itself is a complex in nature, and it has various properties. And when we talk based on the Newton's law, that the fluid can be categorized in two parts. One is Newtonian and another is non-Newtonian nature in form of. So that means if the fluid is following the Newton's law, which is stress is directly proportional to rate of strain, and when the constant will come, that is the viscosity of the fluid, and based on the viscosity of the fluid. Just a minute, one call is coming. Then we'll. Sorry, there was some call, so I could not continue. So there are two type of fluid. One is Newtonian and another is non-Newtonian, and their models are available in the literature. So here we have consider one model which is based on the shear thinning and the shear thickening behavior. That's why it is necessary to know that what is the shear thinning and what is the shear thickening. So shear thinning is the non-Newtonian behavior of the fluids, which viscosity decreases under the shear strain, and sometimes it is also known as a pseudoplastic behavior. That is in different form. If we talk about some examples, so it is just like a ketchup and blood, paint and nail polish, other things. Then when we talk about the shear thickening is also known as in the form of dilatant material, and which is again defined in the form of viscosity. If viscosity increases with time, then my voice is coming, Dr. Das.
Sir,
एक मेल जो है ना मिनिस्ट्री को कर दो, सेक्रेटरी PS टू सेक्रेटरी, एक मीटिंग के लिए मंडे को सर से ना। हाँ
सर वहाँ मीटिंग करेंगे।
हाँ तो एक बार बात कर लो, बात करके मेल कर दो। So I'm extremely sorry, there was some important call, so I could not discuss. So again, these two properties are very important in the case of this. And when we see the nature of shear thinning and the shear thickening behavior of the fluids, you can easily see that what is the nature when we plot the graph between the deformation and the relaxation time. There is some different type of nature which you can see that if the nature is vertical straight after this level, then there is a elastic property, and when it is like a straight line, then it is the Newtonian fluid, and in between there is a curve which shows the linear viscoelastic nature. And this is another curve which is between shear stress and rate of strain, that you can see easily that how we can define the different type of fluid model and how many non-Newtonian natures are there. So if the curve is passing through the origin, but it is not a straight line, then it is in the form of non-Newtonian, and it can be described in the form of pseudoplastic and dilatant. So this dilatant nature is shear thickening, and the pseudoplastic is the shear thinning. And here also, if there is a plasticity in the fluid, then it comes in the form of viscoplastic, and you can easily see that if the line which start from the yielding stress is in the form of Bingham plastic, and again we can categorize two different type of viscoplastic fluid, which is the thixotropic and rheopactic form. And when if it is in the form of curve, which is the axial line, that is the ideal fluid, and in the nature, or if we talk practically, there is no such type of fluid which exists in the nature in the form of ideal fluid. And again, when we talk about the vertical axis, if a curve is like this, then it will be purely plastic fluid. There is no deformation after putting any type of stress or any type of. So this type of, yes, Dr. Das, am I audible? Okay. So these are some other graphs which clarify the different nature of different fluid behavior, and you can see that when we plot the graphs between the shear stress and the shear rate, what type of nature will come for the different type of this. Again, when we talk this equilibrium position of the shear thinning and the shear thickening behavior, you can see that if there is a viscosity at equilibrium level, and when there is a deformation, and you can see that how it will convert or transform from shear thinning to the shear thickening form. So this is the level of shear thickening, shear thinning, and this is the level for the shear thickening. So when the particle or molecules level, if there are some changes due to the external forces, and if viscosity change with this, then the nature will also change. And you can see that when we plot the graph between the shear stress and the viscosity, the graph will look like that. Like in the equilibrium, it will be the straight line, and when the shear thinning nature, then it will go down, and again it will go up if fluid is having the shear thickening behavior. So these are the some geometrical or physical nature of the shear thinning and the shear thickening nature of the fluids, and based on that you can see that how the chemically or molecule change from shear thinning to shear thickening behavior. So these are the basic concept about the shear thinning and the shear thickening behavior of the fluids. And based on that, if we talk about some models, then one of the model which is very very applicable in the case of biological fluid, especially blood, then we can consider the Carreau fluid model, where the role of shear thickening and the shear thinning will come based on the value of n, because n is the fluid index, and based on that This Jeffrey fluid model is a visco elastic model. This has no shear thinning and shear thickening behavior, but it has the viscosity as well as elasticity. When we talk the Bingham plastic, then again it has the plasticity, it has the viscosity, but there is no concept of shear thickening or shear thinning. But when we generalize this viscoplastic nature in the form of Herschel-Berkeley model, and when the Powell law model comes in this viscoplastic model, then this again will show the shear thinning nature and the shear thickening nature of this particular fluid. Then again some other type of non-Newtonian model can be used, like Powell law model, which is the basically non-Newtonian model in the form of power of the rate of shear. And then Cisco model and the cross model can also be used for the different type of rheological property of the fluids. And researchers are using various model to cover the maximum rheological property effects in the fluid flow. So these are some different type of models which we have shown here. But there are other models available in the literature that can be considered in the fluid flow, and some of the model which are especially used for the blood flow that can also be considered when you are going for the hemodynamics, analysis of hemodynamics or analysis of the blood flow. So these are some other curve behavior which you can see that what is the nature when we plot about shear rate and the shear stress and the particular type of examples we have considered, and this is available in the literature based on that. Then we talk about some pumping mechanisms. So there are, in the mechanical engineering, there are two types of pumping mechanism. One is the mechanical pumping and another is the dynamic pumping. And some of the example which you can see that if it is the syringe pump and the air compressor, it comes in the mechanical pumping behavior. But when we talk about the electroosmotic pump based on the electroosmosis mechanism, then it comes in the dynamic pumping form. Then we can think about some natural pumping mechanism which is also creating the pressure to create the pressure for movement of some biological flow, and which you can see that if you see first video where when the people are eating or swallowing some food, then it enters from the mouth and through the esophagus or food pipes it enter into the stomach. And how you can see there is no external force inside this food pipes, but there is a natural pumping process which can be seen that there is a muscle contraction and relaxation, and this is a continuous process of this muscle contraction and relaxation that is known as the peristalsis, and this is the natural pumping mechanism. And it does not work if you can see that it is a vertical form, so maybe due to the gravitational force, but it does not. If you are in the horizontal form and you are taking some foods, then same procedure will be seen, because this is the natural pumping mechanism, and it is known as in physiology it is known as peristalsis, and there is no effect of any other external force. Even gravitational force is not playing role in this movement. Second, if we talk, which is everyone is aware about this, due to the heart pump, circulatory system of the body will work, and the blood is flowing throughout the body through arteries, arterioles, capillaries, and the veins, venules. So there are so many blood vessels, different type and different geometry and different diameters, and the blood is flowing through those geometry only due to the heart pumping, and the heart is pumping in the same position. You can see in the vertical or horizontal form. This is the progressive propagation, but this is the vertical or position is same, but it is pumping like the different form if you compare the both pumping mechanisms. So we have developed various model based on the peristaltic pumping as well as the heart pump also. So heart pump will work in the form of membrane pumping. So here we'll discuss about how the membrane pumping will work mathematically and how it will be applicable for this model. If you see the breathing process, there are two type of process. You can see that one is a closed circulatory system and another is the open circulatory system. If capillary system is present and no respiratory fragment are present, then this type of pumping mechanism will be working. And if capillary system is absent and the respiratory fragment are present, then this pumping, this is the membranes different position, and see how we can take the breath and how oxygen enters into the body and the carbon dioxide this. So yellow color, you can see that how the oxygen enters into the lungs and then this CO2 is exiting from the lungs. So this is the all about when we talk about oxygen and carbon dioxide, this is gases, and these gases are also fluid in the form of compressible fluid. And when we talk about the blood and the other liquids in the body, that is in the form of incompressible fluid. So both type of fluids are available in the body, and both type of flow, like incompressible fluid flow and compressible fluid flow, both application are available in the biological flow transport phenomena. So what type of concept or principle of the fluid dynamics you can use for the particular application, that will be applicable for this. So based on this are motivated from this pumping, natural pumping mechanism, we have developed the mathematical formulation for the membrane pumping mechanism, and you can see that at the same position how this pumping is occurring. And this one is the simulation of this particular equation, and this equation when we simulate in the MATLAB, you can easily see that this is the, so you can use this particular membrane equation at the upper wall, and the same you can use at the lower wall, or you can use is at the various point. Some of the model we have used multi-membrane pumping mechanism. So in that way also you can use the different position, and you can see that how much pressure will occur, because when there is a pumping at a particular point, then there is a creation or generation of the pressure, and when there is a generation of the pressure, then there is a fluid flow, because fluid is flowing due to the difference of pressure, or due to the negative pressure gradient, or due to the, if inlet is at high pressure and outlet is at low pressure, then there is a fluid flow inside the channel. So if there is a creation of the pressure at a particular point, then it will working as a pumping mechanism. And you can see that there are two type of function which we have used for this particular membrane equation, that is a spatial function and temporal function. So temporal function will be based on the time dependent, and the spatial is based on the spatial coordinate system or distance function. So based on that, we have sketched the geometry of this particular model, that is known as a membrane based pumping flow design, and this mathematical equation we have considered, and this particular expression we can use as a lambda membrane, or this is the spatial temporal function of the membrane equation that you can see. And these are the different position, different time, and there are two type of phases which occurs during this oscillation or propagation, that you can see in the form of compression phase and the expansion phase. So compression phase and expansion phase we can define based on the time, and if time is one cycle and it is from 0 to 1, so 0 to half it is the phase of compression, and from half to 1 that is the phase of expansion. So that can be this. And as I told that in this model we have considered the carrier fluid, which is having the shear thinning behavior when the n is less than 1, and the shear thickening behavior when n greater than 1, and this fluid will be from 0 to 1. So that is the motto of this model, and this is the well established model of the fluid for the shear thickening and the shear thinning. So this model we have considered, and then you can see that what is the property of this model. It behaves as a Newtonian fluid with viscosity at 0 shear stress and infinite shear rate, and it behaves as a power law fluid at the intermediate shear stress. So this is a more generalized form of power law fluid as well as Newtonian fluid. So it has both cases depending upon the different particular limitation. And then we have used the concept of mass conservation, which is derived in the form of continuity equation, and the momentum conservation, which is derived in the form of momentum equation. And then we have used the standard procedure for solving the governing equation, which is based on the non-dimensionalization or scaling, or sometimes you can use the similarity transformation. So what is the advantage of this? Because all this physical equation which we are deriving, there has some property. What type of properties are there? It is satisfying the dimensional homogeneity. Dimensional homogeneity means each term is having the same dimension. But when we are using the scaling analysis or non-dimensionalization, then we can easily reduce all the parameters in the form of non-dimensional, and when all the parameters will become in the form of non-dimensional, then it will be the set of partial differential equation in this particular case, and the set of partial differential equation can be solved by using the standard approach, which we know that which we are using to solving the set of partial differential equation. And these are the stress component in the different plane, like xx plane, xy plane, yy plane, and these are the expression, and this expression we use in the momentum, axial momentum equation. This is the axial momentum equation, and this axial momentum equation, when we substitute, we have the pressure gradient in the form of this, and then we can derive some physical quantities which are important in fluid dynamics or flow analysis, that we can easily define, like volumetric flow analysis, which we can use from lower channel to upper channel, and this velocity, axial velocity, can be integrated with respect to y, and then we can use the boundary condition, and this boundary condition is the sleep condition. Again, there are two type of boundary condition used in the fluid flow. One is no slip. No slip means if the velocity at the walls are 0, then it is the no slip condition. When there is some velocity at the walls, that is no slip condition. So here we have considered the slip boundary condition. That means we have assumed that there is some velocity at the walls as well. So based on that, we have again used the standard method for the solving partial differential equation, that is perturbation technique or perturbation method, and which is in the form of series solution, and that approach is very applicable to solving such type of. So we assume this pressure term in the form of series, then volumetric flow rate, then axial velocity, and then we have compared the terms with power of this WE, Weissenberg number, and then we have the different set of partial differential equation with respect to the 0th order, first order, second order, like that, and then we can derive the axial velocity component in the form of this U0, U1, and then we can take the sum of this, because it is the series solution, so we have to truncate up to some orders. That's why U0 and the U1 up to second order we have considered this solution, and based on that we have also derived the pressure, axial pressure, and then this is the sum of u0 and u1. You can see that how we can express the axial velocity in the form of this, and then we can also find the wall shear stress, like how many stress shearing stress at the wall will occur. That will also be derived. Then stream function is another component which is derived from the velocity field, and from the velocity field we have also derived the stream function in the form of this. So that type of expression we can do, and then we can see the numerical results based on the derived solution by using the perturbation technique, and then by using the MATLAB coding we can easily see the graphical results in different form, and what type of effects of the parameters involved in the model, that can also be discussed. So this is the one of the result which you can see that this is the membrane where we have fit in our model, and this is the compression phase. This is the bidirectional phase. That means it is the time at t is equal to half, and this is the expansion phase. So different phases of the membrane can be seen by these figures, and then we have seen that how the pressure will generate and what will be the pressure distribution with respect to the spatial as well as temporal coordinates. So you can see that this is the x direction, this is the time, and with respect to the axial length of the channel and with respect to time, and for different Weissenberg number, that W is equal to 0, it means it work like a Newtonian fluid, and when it is not 0, then it will work as a Carreau fluid. So both comparison, because Newtonian fluid is a basic fluid model in fluid dynamics, which when the people are working on that, a new concept or new model, if they want to generate, then they are using the Newtonian fluid, then further extension with the help of non-Newtonian model can be done. So our first model also we have developed for the Newtonian, then many non-Newtonian model with using the non-Newtonian model we have derived. So this is one of the model which is published in physics of fluid, and this you can see that these are the results which you can see that how the pressure distribution along the axial and along the temporal with respect to some fixed value of the other parameters. So that you can easily see. Then there is a comparison of the rheological behavior like shear thinning, Newtonian, and shear thickening. So based on that you can also see, and this is the sleep condition, because this is the value sleep parameter, Kn is the sleep parameter. So we have seen two different cases. One is if this sleep parameter is 0, then it work is as a no sleep condition. If it is not 0, then it is a sleep condition or sleep parameter, or there is some velocity or there is a sleep velocity. That velocity is also known as a sleep velocity. So that you can see that how much parametric difference can be seen from this figure if the fluid behavior is different. Like if fluid is a shear thinning, then it will in this form, then Newtonian, then shear thickening. And the same thing we can see for the another case which is first is a compression phase, another is the expansion phase. So this figure is for compression and this is for expansion. So both phases, sleep, no sleep, Newtonian, non-Newtonian, then shear and shear thinning and the shear thickening. So all the comparative example, all the comparative analysis can be helpful when we are doing some applied output or applied problems for the blood flow analysis, and this parametric analysis will help. So this is another you can see that if we are thinking about some bio-inspired pumping devices, so how we can build up or how we can manufacture this smart pumping device based on this membrane mechanism. So this parametric analysis will be helpful, that how we can do the dialysis, how we can do the filtration, or how we can do the mixing of the samples by using this pumping devices. So these parametric analysis are very helpful, and before going to manufacture such type of pumping devices, we have to produce various analysis and various rheological property of the fluids, how they are affecting to the flow, fluid flow. So this is another, you can see that this is the pressure distribution for shear thinning and the shear thickening during the compression phase. And then we have the axial velocity profile with Weissenberg number, with expansion phase, and for the sleep condition. So this is another, you can see. And from this result, you can easily say that the velocity profile is a parabolic. And when we think about the pipe flow, which is the standard result, and the velocity profile is also parabolic. So in this case also, the velocity profile is a parabolic. That means at the center, the velocity is maximum. At the walls, the velocity is minimum. That means our model is validated with the standard result, which is already reported and tested in the fluid dynamics problem. This is another analysis for the axial velocity contour plot, and at the membrane region, you can see at the membrane region how the streamlines will be shown, and how the velocity field will be there. That can be shown from this contour plot for the axial velocity. Then again, this contour plot for the velocity field for different type of fluids like shear thinning, Newtonian, and the shear thickening can be seen from this result. And you can see that how this region work for the proper fluid flow and controlled fluid flow, because this pumping mechanism can be controlled by some parameter, that is the membrane parameter, and that membrane parameter will work what type of pumping devices you can develop, and based on that control pumping mechanism, you can control this flow analysis. So this is another result, like we have derived the expression for the wall shear stress. So how much shearing at the walls due to this fluid flow will come, that can also be seen from these two figures. And different cases, like this is the lower wall, this is the upper wall, and this is the center of the walls that you can see, or center of the channel that you can see. And then we have also calculated the value of this shear stress for different value of Weissenberg number. And this is another case which you can see different position. A is for x is equal to 0.3 and B is x is equal to 0. So for both cases, we can see that how much difference will come. And then again, we have plotted one contour plot for distribution of wall shear stress for different type of fluids, that is shear thinning and the Newtonian and the shear thickening. And you can see the ranges of this, and based on the ranges, we can analyze that which fluid is more easier, or where the shear stress is more for the particular fluid, or where shear stress is less for that particular fluid. So that this numerical analysis are very important, and based on this all discussion, we can reach up to the concluding remarks. And that you can see that we have given this sequence for the pressure difference, like pressure difference for the shear thickening is more as compared to Newtonian, and it is also more as compared to the shear thinning. And again, if it is a no sleep condition, then pressure will be more as compared to the sleep condition. So this sequence can help for the application purpose. And again, a pattern of the axial velocity is recorded in the form of this, like velocity for the no sleep condition is greater than velocity with the sleep condition. And in both cases, like whether the fluid is shear thickening or shear thinning, then Weissenberg number will also play the important role for the fluid flow analysis. Another sequence we can see for the velocity, axial velocity, that if it is a Newtonian nature, then pressure will be more, and then when pressure will be more, means membrane will generate more pressure, or membrane, we can conclude in another way that this membrane pumping will easily transport the Newtonian fluid as compared to the non-Newtonian, and this is another sequence for the wall shear stress. So this is the one of the model for the application of biological flow transport phenomena based on the membrane pumping. If there is any queries, these are some references. So thank you very much. If there is any query, then I will be happy to discuss on this topic. So thank you so much for your patience and listening. I'm very sorry. In beginning, there was some disturbance due to some important call, but I finished my talk within time, I think. So if there is no query, you can write to me at my email ID. I will be happy to reply those comments. So thank you very much.
Okay, thank you. Sorry, I can't share my screen. I'm having a problem sharing my screen. It's not letting me share my screen. I can't, it's not letting my computer won't let me share my screen. Do you have, can you upload, I sent you the slides. Can you share is it possible for you to share the slides?
Sir, it could be shared only through your end.
Pardon? Is it possible for you to, I sent you my slides, is it possible for you to, I'm having a problem sharing the screen. Is it possible, you must grant permissions.
Sir, there is an option available in the 3 dots to share your screen. It is not possible for the host to share your screen, sir.
Okay, but it's not letting me. I'm trying. I can see the thing, but it's not giving me 3 dots. I can't. Settings.
There are some options like settings, report upload, problem, sock, caption, share
Settings.
screen, in call message,
Captions.
yeah, there you
I
can
don't.
find.
I can see the share screen button, but it says that it's saying allow Google Meet to share your screen, to share window. Okay, choose content to share. You must grant permissions in order to share your screen. Select Safari settings. Yeah, I know. I can see that. I know, but it's not letting me. I've done that. Allow to share screen. And it says,
exit first. Please exit first and then rejoin the meet.
Sorry.
Can you please first exit and then rejoin the meet? Then it may come.
I don't understand.
First, you must exit from the Google Meet, then rejoin the Meet again. Then try for the presentation.
I don't think that'll work, but I'll try. Okay. Safari to update permissions. Safari settings for this website. Safari settings for Google Meet. Use Reader when available. Okay. So dismiss. So I'll leave it. Okay. It's still not letting me. It's not letting me. It's not. I've tried doing that. It's not letting me. It says. It says, choose content to share. You must grant permissions in order to share your screen. Select Safari settings for this website. It's not allowing me to share my screen.
Sir, if you can,
তোমার এন্ডে কোনো রেস্ট্রিকশন দেওয়া আছে হয়তো আউটসাইড ইন্ডিয়ার জন্য, সেটা কিছু তাহলে
sir, you can share the PDF of the presentation to Krishna Padadas. He will share his screen and you will deliver your lecture through.
I've already done that. He's got a version of, but he said he. I've already sent it. You should already have it.
Yeah, Krishna sir, please share his PPT and sir will deliver the talk.
Do you have my PDF? Krishna Pada, do you have my PDF? I sent it